Some comets drift, others blaze. But the interstellar visitor 3 Atlas embarked on a journey unlike any other. It inexplicably decelerated on its path toward the sun, only to dramatically reverse course and accelerate. Before you dismiss this as conjecture, consider this. We possess new imagery that corroborates this astonishing phenomenon. Allow me to elaborate. Initially, it expelled gas directed towards the sun, as if actively resisting gravity's pull. Then, weeks later, it executed a startling reversal, expelling its jets in the opposite direction, akin to a dormant spacecraft suddenly awakening. Astronomers have termed this a jet inversion. A vibe views it as something profoundly significant, and tonight we will explore why. Because if this was a deliberate maneuver performed near its closest solar approach, then an intelligent agent has effectively utilized the sun as a gravitational slingshot. Please, stay with us until the conclusion to grasp what 3 Atlas might be communicating about its origins and perhaps about ourselves. If these enigmas have you as captivated as they have me, don't merely observe. Join the investigation. Hit the like button and subscribe to ensure you don't miss a single unfolding revelation in this evolving narrative, documented in real time. In the comments below, tell me your location, the current time there, and whether you believe we are privy to the complete account of the events transpiring above us. And if you wish to amplify this message, share this video across X, Facebook, Reddit, or even with those individuals who still gaze upwards at the night sky. You are the reason we can continue to pursue the extraordinary. For that, we are profoundly grateful. Part 1. Groundbreaking disclosure. What you are witnessing is an unprecedented behavior from a comet. Displayed before you are 2 images presented side by side. The first, captured by the Hubble Space Telescope on July 21, 2025, reveals a comet radiating with unusual intensity. Its emission pointed directly at the sun. The subsequent image, acquired weeks later by the Nordic Optical Telescope, shows the same celestial body, but now its luminous tail streams away from the sun, as any well-behaved comet would. Between these 2 distinct moments, a fundamental shift occurred. Something deemed impossible transpired with the interstellar object 3 Atlas. The assertion might sound so simple as to be easily disregarded. Comets are in constant flux, aren't they? They develop tails, brighten, and fragment. We have observed their cosmic ballet for centuries. However, this instance is markedly different. This entity appears to have completely reoriented its jet emissions. In July, it was expelling matter towards the sun, manifesting what astronomers designate an anti-tail, a sunward luminescence that defied the conventional physics of solar radiation pressure. Then, as summer transitioned into autumn, observers noted the fading of that forward-directed emission, while a new tail emerged, extending away from our star, precisely as dictated by established physics. You might surmise this is merely a trick of perspective, an optical illusion caused by Earth's shifting position relative to the comet's path. Such apparent distortions are common in astronomy. A galaxy viewed edge-on from one vantage point appears face-on from another. It's all about your position within the cosmic panorama. Yet, the scientists meticulously tracking 3 Atlas have systematically ruled out simplistic explanations. The timing is incompatible with a purely geometric effect. The composition of the ejected material demonstrably changed between the observed periods. The morphology, the technical term for the tail's shape and structure, evolved in a manner suggesting an internal transformation within the object. The Nordic Optical Telescope monitored this metamorphosis throughout July, August, and September. Sequentially, image by image, they meticulously documented the gradual weakening of the sunward jet and the concurrent strengthening and elongation of the anti-solar tail. This was not an instantaneous alteration, akin to flipping a switch. It was a protracted transition, a slow reversal unfolding over several weeks as the comet continued its hyperbolic trajectory toward the inner solar system. And it is precisely this gradual nature that presents such a profound challenge to conventional explanations. Here, it is essential to comprehend the physical processes at play. When matter is expelled from a comet, it carries momentum. It exerts a force. If you are ejecting gas and dust towards the sun, you are generating thrust in that direction, which consequently impedes your forward motion relative to your orbital velocity. If you reverse this expulsion to point away from the sun, you then begin to accelerate in the opposing direction. For an object following a precisely calculated trajectory through the solar system, such a reversal should manifest in its motion. Its orbit should diverge from the purely gravitational path predicted by the equations of Newton and Einstein. The object would be found in a slightly different position than celestial mechanics alone would indicate. Yet, here lies the enigma. 3 Atlas is not exhibiting significant non-gravitational acceleration. Its trajectory aligns with predictions based solely on gravity, within the margins of observational error. This implies one of two possibilities. Either the jets are perfectly balanced, expelling material equally in all directions, thereby canceling out opposing forces, or the object is of such immense mass that the recoil from its outgassing is negligible compared to its inertia, or an entirely different, as yet unconsidered phenomenon is at work. Allow me to illustrate what makes this observation so extraordinary. Visualize vectors, arrows indicating the direction of material ejection. In July, that arrow points sunward, counteracting the solar radiation that typically pushes comet tails away. Now, observe as we advance through time. August, early September, late September. The sunward arrow diminishes. A new arrow emerges, pointing precisely in the opposite direction, away from the sun. While the comet's position relative to Earth and the sun does shift during this period, it does not do so in a way that would create this apparent reversal solely through projection effects. Astronomers have annotated these images with overlaid geometric representations. Earth here, the sun there, the comet following this specific trajectory. The viewing angle does indeed change, but when this perspective shift is mathematically corrected, when we account for how projection can deceive the eye, the reversal persists. Something physically altered regarding the location and manner in which this object was releasing material into space. The immediate question on everyone's mind is whether we are observing a highly unusual manifestation of normal cometary behavior, or whether 3 Atlas is exhibiting characteristics that necessitate a more unconventional explanation. The most conservative interpretation posits compositional changes as the comet encounters increasing solar warmth. Different types of ice sublimate at varying temperatures. As the outer layers heat and vaporize, deeper layers with distinct chemical compositions are exposed. In principle, this could alter the pattern of outgassing, sufficiently to reverse the dominant expulsion direction. However, another interpretation exists, one that borders on science fiction, but originates from serious scientific inquiry, published in peer-reviewed journals. What if this is not random outgassing at all? What if the reversal is a controlled, deliberate act, a maneuver executed by an object that is not entirely natural? Before you dismiss this as sensational speculation, understand the credentials of those proposing this hypothesis and the evidence they cite. The engineered probe hypothesis, as it is formally designated in academic papers, is predicated on observable signatures. If the sunward emission represented braking thrust, and the subsequent tail directed away signifies forward acceleration, timed to coincide with the comet's closest solar approach, then we are witnessing behavior more akin to trajectory adjustment than passive ice sublimation. The implications here extend far beyond a single anomalous comet. If 3 Atlas is a natural phenomenon exhibiting behavior we have never before documented, It expands our understanding of the capabilities of interstellar objects, their composition, and the processes that occur when bodies from other star systems traverse our cosmic neighborhood. If it is something else, if these signatures of an engineered object withstand rigorous scrutiny, then we are on the precipice of a discovery of unparalleled historical significance. We have weeks, not years, to ascertain the truth. The object reaches perihelion, its closest point to the Sun, on October 29, 2025. This moment will represent peak heating, maximum thermal stress, and heightened activity. What transpires with 3I Atlas during this passage will either confirm it as an extraordinary, albeit natural comet, or deepen the mystery into something that demands answers we are not yet equipped to provide. Part 2. Quantitative constraints and dynamics. The numerical data present a compelling narrative, commencing with its mass. Between July and October of 2025, 3 Atlas released approximately 2 million metric tons of material into space. Reflect on that figure for a moment. 2 million tons. That is equivalent to the mass of roughly 3 Empire State Buildings vaporizing into the vacuum, propelled by solar heating and internal pressure over a mere few months. Astronomers arrive at this figure through meticulous measurement of its brightness and composition. As dust and gas scatter sunlight, they become detectable through the luminescence they generate. Telescopes measure this brightness across various wavelengths, applying conversion factors that account for particle size, reflectivity, and geometric distribution. This brightness is then integrated over time, tracking the volume of material continuously streaming away from the nucleus. The resulting metric is a mass loss rate, escalating from grams per second to kilograms per day, culminating in millions of tons over the observation period. This loss of mass inherently generates thrust. It is an inescapable consequence. Every action elicits an equal and opposite reaction, a principle of Newton's third law that applies as reliably in the vacuum of deep space as it does here on Earth. When a comet expels gas and dust, its nucleus experiences a recoil akin to a firing rocket engine. For typical comets, this propulsive effect is quantifiable. It manifests as deviations from their purely gravitational orbits, minute accelerations that astronomers categorize as non-gravitational forces in their orbital calculations. However, 3 Atlas displays minimal non-gravitational acceleration. Its trajectory aligns precisely with predictions based solely on gravitational influence. The orbital residuals, those minor discrepancies between its predicted and actual positions, remain within the statistical noise of measurement uncertainty. This absence of detectable recoil imposes stringent limitations on the possible explanations. Allow me to guide you through the calculation that underscores its significance. If the rate at which mass is being ejected is known, along with the velocity of that material as it departs the nucleus, the thrust force can be determined. Thrust is calculated as mass flow rate multiplied by exhaust velocity, the fundamental rocket equation as applied to a comet. The exhaust velocity is contingent upon the properties of the sublimating volatiles, with different substances expanding at distinct speeds. Carbon dioxide molecules, energized by the sun, accelerate away more rapidly than heavier dust particles carried along by the gas flow. Employing reasonable estimates for these velocities, perhaps in the range of a few hundred meters per second for gas, and slower for dust, and multiplying by the observed mass loss rate, yields a thrust force. Subsequently, calculating the acceleration produced by that force, by dividing force by mass, reveals the critical constraint. For the observed lack of orbital perturbation to be plausible, the nucleus must possess sufficient mass such that this thrust has a virtually imperceptible effect. The minimum estimated mass converges at approximately 33 billion metric tons. 33 billion. The uncertainty range is substantial, attributable to our incomplete knowledge of the precise dust velocity, the degree of directional versus isotropic outgassing, and the exact ratio of gas to dust. Nevertheless, even accounting for these variables, the lower bound comfortably resides in the tens of billions of tons. What kind of object possesses such a mass? Assuming a density comparable to typical comet nuclei, around 600 kilograms per cubic meter, a porous mixture of ice, dust, and rock, we can infer its dimensions. The calculation suggests a body several kilometers in diameter, comparable to some of the larger comets that have been studied in close proximity by spacecraft. Comet Hale-Bopp, the spectacular visitor of the mid-90s, had a nucleus estimated at roughly 60 billion tons. Comet Halley, the most renowned periodic comet, has an estimated mass of about 220 billion tons. 3 Atlas occupies the lower end of this spectrum, but still qualifies as a substantial celestial body. The uncertainty bands warrant careful consideration, as they highlight the extent of our current knowledge gaps. If the dust particles are moving at higher velocities than assumed, the mass estimate decreases. If the outgassing is more anisotropic, concentrated into narrow jets rather than dispersed uniformly, the recoil might be directionally biased in ways that partially counteract, thereby weakening the mass constraint. If a greater proportion of the ejected mass consists of fine dust rather than gas, the momentum transfer shifts, as dust accelerates more slowly and may contribute less thrust per unit mass. Envision a Monte Carlo simulation now displayed on your screen. Thousands of model runs explore diverse parameter combinations within their plausible ranges. Each run generates a mass estimate. The distribution of these results shows a peak around 33 billion tons, but it broadly spreads across a factor of 3 in either direction. This represents the honest uncertainty inherent in astronomical inference, translating observed light into physical characteristics across hundreds of millions of kilometers of space. 3 distinct scenarios could account for the minimal non-gravitational acceleration. Firstly, the object is genuinely massive enough that its outgassing thrust is insignificant. This is the most straightforward interpretation, requiring no extraordinary assumptions, merely a large comet shedding material in proportion to its size. Secondly, the outgassing might be unusually symmetrical, with jets firing in multiple directions such that the net force averages close to 0. Some comets achieve this through active regions on different surface areas, producing thrust vectors that partially cancel each other. Thirdly, a non-cometary mechanism might be at play, some process that deviates from the standard sublimation-driven model. This third option ventures into speculative territory, yet it is speculation grounded in observational constraints. If 3 Atlas were maneuvering using a controlled propulsion system, one would anticipate the thrust to be balanced or variable in ways that do not result in random orbital deviations. An engineered object maintaining a specific trajectory would minimize detectable non-gravitational forces beyond its intended maneuvers. The mathematical analysis does not definitively prove this interpretation, but crucially, it does not refute it either, which is sufficient reason to keep the question open. The estimated size also carries significance for another reason. Interstellar space is a harsh environment. Cosmic rays continuously bombard any object traversing the galaxy. Over millions or billions of years, these high-energy particles erode surface materials, alter chemical compositions, and induce radiation damage. Smaller objects are more profoundly affected due to their limited mass relative to their surface area for absorbing such punishment. A body several kilometers in diameter would have possessed sufficient mass to survive its interstellar voyage relatively intact, preserving a substantial inventory of volatiles that can now become active as it enters the warmth of the solar system. Contrast this with Oumuamua, the first confirmed interstellar visitor, which was likely only hundreds of meters in size based on its brightness and assumed composition. Oumuamua exhibited significant non-gravitational acceleration, despite no detected outgassing, a puzzle that generated years of debate and numerous competing hypotheses. 3 Atlas, being considerably larger, should produce observable outgassing if it contains volatiles, and it does. However, the absence of corresponding orbital changes, given its substantial mass loss, presents its own unique enigma. What transpires next hinges on its perihelion passage. The close solar approach will heat the nucleus to its maximum temperature, potentially triggering new outgassing from previously dormant regions. If the mass loss rate escalates dramatically, as is often observed with comets approaching the Sun, we will gain more precise constraints on the nucleus's properties through this enhanced activity. Conversely, if orbital residuals suddenly surge, indicating clear non-gravitational acceleration during or following perihelion, it would signal a shift in the outgassing pattern. The data acquired in the ensuing weeks will either refine these mass estimations or reveal novel anomalies that demand explanation. Part 3. Physical and compositional modeling. The physics of ice offers a comprehensive explanation, provided we allow it. Abraham Lowe and Andrew Kito, 2 astronomers who have dedicated significant thought to 3 Atlas, have proposed a model attributing the jet reversal to compositional shifts in the sublimating volatiles. Their argument is rooted in fundamental principles governing the behavior of different ices at varying temperatures and distances from the Sun. Consider carbon dioxide ice. It transitions directly from a solid to a gaseous state, sublimes, at temperatures well below the freezing point of water. Even at the frigid distances beyond 3 to 4 astronomical units from the Sun, carbon dioxide molecules can break free from their crystalline lattice and escape into space. This gas expands rapidly, and in doing so, it entrains dust particles, drawing them along through collisions and momentum transfer. These liberated dust grains subsequently become subject to solar radiation pressure, the gentle yet persistent force exerted by sunlight, which impacts smaller particles more significantly than larger ones. Now, contemplate what occurs as the comet journeys inward, closer to the Sun's warmth. The carbon dioxide sublimes more vigorously, but eventually the surface layers rich in carbon dioxide become depleted. Deeper material is exposed, and this underlying material possesses a different composition, dominated by water ice, interspersed with refractory dust. The rocky and carbonaceous particles that do not sublimate, but rather remain behind or are mechanically dislodged as the surrounding ice vaporizes. Water ice necessitates higher temperatures for efficient sublimation, activating closer to the Sun in the inner solar system where heating intensifies. The dust released by water sublimation exhibits distinct properties compared to dust entrained by carbon dioxide. The distribution of grain sizes may differ. The release velocity might be lower because water vapor expands with less energetic force than carbon dioxide. The survival distance, the extent to which particles travel before either decomposing under solar heating or being dispersed by radiation pressure, varies based on composition and size. This is where the model becomes particularly insightful. Lowe and Cato propose that this transition from carbon dioxide dominant to water dominant sublimation can reverse the apparent direction of the emission. During the carbon dioxide phase, smaller ice-coated grains with short lifespans scatter light efficiently at optical wavelengths. These particles, released early in the comet's approach, might create a forward-scattered glow visible from Earth's perspective, appearing as a sun-facing anti-tail. As the process shifts to water and refractory dust, larger particles with different scattering characteristics become predominant. These generate a more conventional tail, pushed away from the Sun by radiation pressure. The timing aligns precisely with the observed phenomena. 3 Atlas was situated at approximately 3 to 4 astronomical units from the Sun when the anti-tail was most pronounced. This is precisely the distance range where carbon dioxide sublimation should be active, while water ice remains largely inert. As the comet descended through 3 astronomical units, progressing towards its October perihelion at 1.356 astronomical units, the transition to water-dominant activity would naturally occur. The images captured by the Nordic Optical Telescope, documenting the tail reversal in August and September, perfectly encompass this transitional period. Imagine a cross-section of the comet's nucleus presented on your screen. The outer layers, exposed to the harshness of space during the object's extensive interstellar voyage, are enriched in carbon dioxide ice because it is more volatile, more likely to have been retained near the surface. Deeper still, water ice prevails because it possesses greater refractoriness and is less susceptible to vaporizing during the object's prolonged period of dormancy between stellar systems. As solar heating generates a vaporization front that advances into the nucleus, this front intersects the compositional boundary. The gas release mechanism alters, and consequently, so do the observable characteristics of the comet and its tail. This concept finds validation in the observed behavior of solar system comets. Astronomers have documented comets exhibiting cyclical fluctuations in their activity, with different sectors becoming active or dormant as the body rotates and its distance from the Sun changes. Comet Hale-Bopp, that colossal visitor from 1997, displayed multiple distinct streams emanating from various active zones, each expelling material with slightly differing compositions and at varied intervals. The accumulated knowledge from decades of cometary research indicates that these celestial bodies are intricate, layered structures capable of unexpected actions as thermal energy penetrates their inner regions. However, Comet 3I 2023A3 appears to undergo a more sudden alteration in its characteristics than is typical for solar system comets. The shift occurred over a span of weeks rather than months or years. Such swiftness suggests either a sharp, internal compositional demarcation within the nucleus, or an unusual configuration of active areas. It is plausible that the initial sun-facing activity originated from a particular surface location that ceased to be active once it surpassed a certain thermal threshold, while concurrently, a distinct region on the opposite side became energized. Comet nuclei are irregularly shaped bodies, often featuring complex topographical features. Steep drops, depressions, and fractured landscapes can concentrate the expulsion of gas in ways that do not mirror the average surface properties. This proposed model generates predictions that are verifiable. If the explanation involving a compositional transition is accurate, spectroscopic examinations should reveal the anticipated modification in gas makeup. Initial observations, when the anti-tail was prominent, ought to display relatively robust emission lines from carbon dioxide. Subsequent observations following the reversal should indicate heightened water vapor and potentially other volatile substances like carbon monoxide, which vaporize at intermediate temperatures. The proportion of dust to gas should also fluctuate, with more resilient material present in the later stages. Some observational evidence corroborates this scenario. Reports suggest that follow-up spectroscopic studies detected compositional shifts consistent with evolving volatile activity. The relative intensity of different emission features changed between July and September, aligning with expectations if the primary vaporizing substance had altered. Nevertheless, the available data remains sufficiently limited that alternative interpretations cannot be definitively discounted. Spectroscopic analysis of faint, swiftly moving objects presents considerable challenges. Limitations in signal-to-noise ratio mean that the subtle spectral lines necessary to confirm the hypothesis are not always discernible. The distribution of particle sizes introduces an additional layer of complexity. The model proposed by Lowe and Keto specifically incorporates the influence of particle size on the object's dynamics. Small particles, ranging from submicron to micron scale, are closely entwined with gas flow and are propelled to high velocities. They also have brief lifespans, as solar heating rapidly vaporizes any volatile coatings. Larger particles, measuring tens to hundreds of microns, are less integrated with the gas, move more slowly, and endure for longer durations. The interplay between these particle populations dictates the visual appearance and spatial distribution within the coma and tail. The model posits that during the carbon dioxide phase, small ice particles are primarily responsible for the optical signature, creating a concentrated bright emission that, under specific viewing orientations, appears to face the sun. In contrast, during the water dust phase, larger refractory particles dominate, producing a more dispersed tail that conforms to the traditional pattern driven by radiation pressure. The abruptness of the transition is attributed to the relatively narrow range of distances over which the compositional boundary is traversed. Deficiencies within this explanation exist, and diligent researchers acknowledge them. The prerequisite compositional layering, while conceivable, has not been directly observed. We have not penetrated the interior of 3I 2023A3 to verify its possession of an outer layer rich in carbon dioxide, overlying an interior abundant in water. We are inferring its structure from its observed behavior, a method that invariably carries inherent risks. The anisotropy of the emission, meaning whether jets are concentrated or spread out, remains uncertain, and the precise distribution of particle sizes, which is crucial to the model's predictions, is inadequately defined by current observations. What observational evidence would conclusively validate or invalidate this model? High-resolution imaging that captures multiple active regions initiating and ceasing activity would be beneficial. Time-resolved spectroscopy, meticulously documenting the transition moment, would refine our understanding of the sublimation chemistry. Polarimetric measurements, revealing alterations in dust characteristics, would test the predictions regarding particle size. Most importantly, continuous monitoring throughout and following its perihelion passage will reveal whether the anti-solar tail persists, intensifies, or yields to new behaviors as the comet experiences peak solar heating. The compositional model represents the most straightforward interpretation, requiring no novel physics or speculative assumptions, but rather the intricate yet understood interactions of ice and dust under solar irradiation. It is the explanation most cometary scientists would favor unless confronted with contradictory evidence. However, as we shall explore, not all are persuaded that ice accounts for the entire phenomenon. Part 4. The alternative hypothesis of controlled motion in an engineered probe. We now venture firmly into the realm of conjecture, albeit with scientific rigor rather than sensationalism. Abraham Lowe and Adam Hibbard, through a series of public statements and technical analyses, have posed a question that most astronomers tend to avoid. What if the reversal of jet activity is not a natural occurrence? What if 3I 2023A3 is executing a deliberate maneuver, altering its trajectory using propulsion that only superficially mimics cometary outgassing? This hypothesis hinges on the timing and directionality of observed phenomena. If the sun-facing anti-tail observed in July served as a braking thrust, subtly propelling the object towards the sun and thereby reducing its orbital velocity, then the subsequent anti-solar tail could signify forward thrust, accelerating the object outward as it completes its swing around perihelion. Such a maneuver would resemble a trajectory correction, akin to the adjustments a spacecraft makes to refine its path through the solar system. Before dismissing this as outlandish speculation, consider the observable indicators that would support it. Firstly, sustained non-gravitational acceleration exceeding that predicted by sublimation models. If the thrust continues for a longer duration than thermal models suggest, the outgassing should persist, or if the acceleration is greater than the observed mass loss rate can account for, that would constitute an anomaly. Secondly, consistent reorientation of the jet axis. While natural comets can exhibit multiple jets, these are typically linked to the object's rotation and illumination pattern. If 3I 2023A3 demonstrates changes in jet direction that do not correlate with rotational or solar heating patterns, that would be peculiar. Thirdly, spectral anomalies. If the emitted material possesses a composition inconsistent with typical cometary volatiles, it would necessitate an explanation. To date, none of these definitive indicators have been unequivocally detected, yet the observations remain incomplete. The object is faint, moving rapidly, and challenging to track consistently. Gaps in the data preclude ruling out brief periods of unusual acceleration or spectral features that may have occurred when no telescopes were observing. The absence of evidence is not evidence of absence, a principle that applies here perhaps more acutely than in most astronomical enigmas. Testing the hypothesis of an artificially constructed object requires prolonged astrometric observation. Astronomers need to ascertain the object's position with extreme precision repeatedly over months and years. Subsequently, these positions are analyzed against orbital models, comparing purely gravitational trajectories with models incorporating non-gravitational forces. The residuals, representing the discrepancies between predicted and observed positions, reveal whether factors beyond gravity are influencing the motion. Minor, random residuals are expected, stemming from measurement inaccuracies and subtle outgassing. Significant systematic residuals, indicating persistent thrust in a consistent direction, would be extraordinary. Polarimetric observations could also provide valuable insights. Dust particles scatter light, and this scattering generates polarization patterns dependent on particle size, shape, and composition. Natural cometary dust exhibits characteristic polarization signatures that vary with the phase angle, which is the angle between the sun, the object, and the observer. If 3I 2023A3 produces polarization inconsistent with known dust types, it would serve as a significant clue. Similarly, high-resolution spectroscopy might detect emission or absorption lines from materials not typically found in comets, such as metals or complex organic compounds, any of which could suggest a processed or manufactured composition, rather than primitive solar system or interstellar ices. Another diagnostic involves trajectory analysis. Is the orbit of 3I 2023A3 unusual in any respect? Does its approach to the inner solar system occur at an angle or speed that appears excessively deliberate or finely tuned? Interstellar objects possess random trajectories dictated by their expulsion from their home star systems and their journey through the galaxy. If the orbit of 3I 2023A3 exhibits a degree of fine-tuning that raises suspicion, defining what constitutes such suspicious refinement remains subjective. With a sample size of only a few known interstellar visitors, we do not yet have a clear understanding of the typical distribution of their orbits. The scientific community's response to this hypothesis has been varied, with a general inclination towards skepticism. Most astronomers favor conventional explanations until compelling evidence necessitates otherwise. The history of purportedly anomalous phenomena that were later explained by natural processes is extensive. Radio pulses were briefly considered potential alien transmissions until the physics of neutron stars provided a satisfactory explanation. Fast radio bursts fueled exotic speculation until observations linked them to astrophysical sources. The default assumption, the null hypothesis, that 3I 2023A3 is an unusual but natural comet, carries a strong initial probability. Nevertheless, Lowe and his colleagues contend that dismissing the possibility without rigorous testing is contrary to scientific principles. Science progresses by exploring hypotheses, even those that are unsettling, and by devising observations to confirm or refute them. The discovery of extraterrestrial technology would be an event of unparalleled significance. It is so monumental that it warrants a more thorough investigation than is typically afforded to fringe theories. The potential cost of overlooking a genuine technological signature due to insufficient scrutiny, a false negative, is arguably greater than the expense of pursuing natural objects mistakenly believed to be artificial, a false positive. This discussion touches upon the sociology of scientific research. How do scientists navigate the balance between open-mindedness and the risk of making career-damaging errors? How does the scientific community manage claims that blur the lines between legitimate inquiry and sensationalism? Lowe's prominent standing and his readiness to engage with the media and the public have amplified these questions. Some peers commend his advocacy for techno-signature research, viewing it as essential for securing funding and public attention. Others express concern that premature speculation undermines credibility and complicates serious efforts in the search for extraterrestrial intelligence. SETI. The risk-reward calculation is stark. If 3I 2023A3 is a natural object, which is the more probable scenario, then this entire endeavor will confirm existing assumptions about interstellar comets and perhaps reveal new insights into compositional diversity. If, however, it is artificial, even with a minuscule probability, we are on the verge of the most consequential discovery in human history. First contact, or at least the initial detection of technology, originating from beyond Earth. That possibility, however remote, justifies dedicated follow-up investigations. What would constitute definitive confirmation? It would require multiple independent lines of evidence to converge. Sustained acceleration, inconsistent with outgassing, spectral features suggesting manufactured materials, and potentially radio or infrared emissions at frequencies and modulation patterns inexplicable by thermal processes. Observations from multiple observatories, analyses by independent research teams, and rigorous statistical evaluations ruling out instrumental artifacts and natural explanations would be essential. The standard for accepting such a claim would be, and rightly should be, extraordinarily high. Proposed follow-up strategies include dedicated space missions. Lowe has suggested launching fast flyby probes on high-energy trajectories to intercept 3I 2023A3 after its perihelion passage and conduct close-up imaging, spectroscopic analysis, and particle sampling. Such missions would be costly and technically demanding, requiring rapid development timelines to capture the object before it recedes back into interstellar space. However, when weighed against the potential payoff, the investment might be justifiable. The critical constraint is time. By the time funding, approvals, and construction are completed through conventional channels, the object will likely have departed. This necessitates the development of rapid response mission architectures, something the space exploration community has not yet established for interstellar targets. Another approach involves leveraging existing assets. Ground-based telescopes can maintain tracking. Space telescopes, if their schedules permit, could offer higher resolution and sensitivity. Radio observatories could be employed to detect potential transmissions. Even if 3I 2023A3 is not deliberately broadcasting, it might emit radio noise resulting from interactions between charged particles and its surface or any internal electronic systems. SETI protocols developed for listening to stars could be adapted to target this nearby, moving object. The timeline is of paramount importance. Perihelion, scheduled for October 29th, will expose the object to maximum heating and stress. If it is a passive comet, we can anticipate increased outgassing, potentially fragmentation if structural weaknesses are present. If it is something else, the close solar passage might activate systems that have remained dormant during its cold approach. The period immediately surrounding perihelion represents the crucial observation window. Following this, 3I 2023A3 will rapidly retreat back towards interstellar space. Its apparent brightness will diminish as its distance from the Sun increases. Eventually, it will become too faint for all but the most powerful telescopes to track, and then it will vanish from human observation forever, unless a mission is dispatched to pursue it. The hypothesis of an engineered probe evokes a sense of science fiction. Perhaps it is indeed so. It is possible we are perceiving patterns where none truly exist, projecting human concepts of spacecraft maneuvers onto the random process of ice sublimation. However, the only definitive way to ascertain the truth is to gather more data, rigorously test the predictions, and follow the evidence wherever it may lead. This is the essence of the scientific method, applicable whether we are studying terrestrial rocks, distant stars, or objects that may be neither. Part 5. The stakes of observation and the temporal constraints. The urgency is escalating with each passing day, drawing us closer to a moment that will either illuminate the nature of 3I 2023A3 or elevate its enigma to the realm of legend. Perihelion occurs on October 29th, 2025, at which point the comet will reach its closest proximity to the Sun, approximately 1 astronomical unit and 356 thousandths, equivalent to about 203 million kilometers. This distance places it well within Earth's orbital path, where solar heating intensifies dramatically. Perihelion serves as the ultimate test. Every model, every speculation, and every measurement discussed thus far will be rigorously examined during the hours and days surrounding this closest approach. The Sun's radiation will bombard the nucleus with peak intensity. If the object contains volatile substances, they will sublimate profusely. If structural vulnerabilities exist, the thermal stress and internal pressure may induce fragmentation. Astronomers have witnessed comets disintegrate at perihelion previously, with dramatic breakups revealing internal structure and composition. The observational challenges are substantial. At perihelion, 3I 2023A3 will be relatively near the Sun as viewed from Earth, necessitating careful timing of observations to avoid the glare of our star and the daytime sky. Ground-based telescopes will have limited windows, either before dawn or after dusk, when the comet is visible above the horizon, but the Sun is sufficiently below it. Space-based telescopes offer advantages as they are not constrained by Earth's diurnal cycle. However, even they must contend with bright background illumination and the potential for instrument damage if pointed too close to the Sun. The Hubble Space Telescope, responsible for the striking image captured in July, operates under strict solar avoidance protocols. It cannot be pointed within a specific zone surrounding the Sun without risking harm to its sensitive instruments. Scheduling observations of 3I 2023A3 requires meticulous planning to ensure the object is positioned sufficiently far from the Sun in the sky to be observed safely. The Nordic Optical Telescope and other terrestrial observatories face comparable, though distinct, limitations related to twilight and seasonal viewing opportunities. Furthermore, the Mars flyby on October 3rd, when 3I 2023A3 passed within range of the red planet, presents another potential observation opportunity. Did Mars orbiters capture imagery? The high-resolution imaging science experiment, known as HiRISE, aboard the Mars Reconnaissance Orbiter, has produced remarkable close-up views of Martian surface features and occasionally directs its gaze towards passing comets. If HiRISE or other Mars-orbiting cameras imaged 3I 2023A3, those photographs would offer an invaluable alternative perspective, helping to resolve ambiguities in Earth-based observations. However, Mars orbiter time is a precious resource, allocated months in advance for surface science investigations. It remains to be seen whether approval was secured to target this rapidly moving interstellar visitor. The most significant findings are anticipated after perihelion. As 3I 2023A3 arcs back outward, Its brightness will initially remain elevated due to the recent outgassing stimulated by solar heating. This period is when astrometric precision becomes paramount. Measuring the object's position every few days will reveal how its motion deviates from its pre-perihelion trajectory. If non-gravitational acceleration suddenly emerges or changes in magnitude, it will provide crucial information about events that occurred during or as a consequence of the perihelion passage. December 19, 2025, marks another critical date: Earth's closest approach. At approximately 1 astronomical unit and 8/10, about 270 million kilometers, the comet will be at its nearest point to our planet. While still a considerable distance, it is close enough for detailed observation. Large ground-based telescopes can acquire high-resolution images and spectra. The James Webb Space Telescope, contingent on its schedule, could provide infrared spectroscopy, revealing compositional details invisible in optical wavelengths. Spectral lines corresponding to water, carbon dioxide, carbon monoxide, methane, ammonia, all common cometary volatiles, along with any exotic species, would appear in JWST's data. The timeline also encompasses periods of potential observation disruption, times when observations are difficult or impossible. Solar conjunction, when the comet appears too close to the Sun from Earth's perspective, creates blackout periods. During conjunction, radio communication can be hampered. Solar interference drowns out faint signals, and optical telescopes cannot be safely pointed in that direction. 3I 2023A3 will traverse conjunction phases as its orbit brings it across our line of sight to the Sun. These gaps in coverage mean that brief events, such as sudden brightening or morphological changes, that occur and then fade while unobserved, might be missed. The evolution of brightness introduces further uncertainty. As the comet recedes from the Sun post-perihelion, its luminosity will diminish. The rate of this fading depends on its continued activity. If outgassing ceases rapidly, brightness will decline swiftly, soon rendering the object too faint for all but the largest telescopes. If activity persists, fueled by subsurface heat retained from perihelion or delayed volatile release, the comet could remain observable for an extended period. Historical cometary behavior exhibits considerable variation in post-perihelion activity. Some fade into obscurity within weeks, while others remain active for months, their tails gradually shrinking but still visible. Coordinated efforts among observatories will be indispensable. Temporal alert networks, initially conceived for tracking phenomena like supernovae and other cosmic events, can be repurposed to monitor objects such as 3 Atlas. When a single observatory detects an abrupt change, notifications are disseminated to other facilities, prompting further investigation. This inter-observatory cooperation has become a standard practice in the field of time-domain astronomy. For instance, the detection of gravitational waves triggers global efforts to observe their electromagnetic counterparts. While 3 Atlas does not possess the same immediate urgency, the underlying principle remains applicable. The primary limitation lies in spectroscopic capabilities. Obtaining a spectrum necessitates concentrating an object's faint light into a narrow aperture and then spreading it across a detector. This process is time-consuming and diminishes the signal strength compared to direct imaging. To effectively observe a faint, rapidly moving target, one requires a substantial telescope, precise tracking, and extended exposure times. Few observatories are equipped to provide this on demand. The schedules for major instruments are often booked months in advance. Securing discretionary time from directors for urgent, opportunistic targets demands compelling proposals and a degree of fortune. Furthermore, the question of what to search for is crucial. If the objective is to test the hypothesis of a naturally occurring comet, the focus would be on its composition, physical form, and how its brightness evolves. Conversely, if the hypothesis being tested is that of an artificially constructed object. Additional observations would be required, including radio astronomy, the search for unusual spectral lines, the investigation of polarization anomalies, and monitoring for any signs of non-random behavior. Each of these investigative approaches necessitates distinct instruments and observational strategies. Given that resources are finite, decisions must be made regarding which tests to prioritize. Public interest introduces another facet to this situation. 3 Atlas has garnered attention far beyond the usual astronomy enthusiasts, sparking discussions in news articles, social media, and even prompting inquiries from governmental bodies. This public fascination can aid in securing telescope time and funding. However, it also introduces a degree of pressure. Astronomers must strike a balance between rigorous scientific inquiry and the public's desire for swift answers. Rushing to conclusions risks inaccuracy, while waiting too long could result in the object fading beyond observational reach before decisive data can be gathered. By December 19th, we will possess months of observational data, with the trajectory precisely mapped. Spectroscopic observations will have characterized any alterations in composition, and high-resolution imaging will have documented changes in its physical structure. The synthesis of all this information will either lead to a cohesive natural explanation, or leave us with residual anomalies that cannot be easily disregarded. This convergence or lack thereof will dictate subsequent actions. If the data corroborate the compositional model, and all findings align with the narrative of a transition from carbon dioxide to water, then 3 Atlas will be understood as a fascinating, yet ultimately conventional, interstellar comet. Scientific papers will be published, conferences will feature relevant sessions, and the object will be added to the growing registry of visitors from beyond our solar system, serving as a data point in studies of populations of small bodies within our galaxy. Science will advance, enriched by the experience. However, if anomalies persist, if the non-gravitational acceleration does not conform to sublimation models, and if spectral features remain unexplained, the discourse will shift. Proposals for dedicated missions will receive serious consideration, and observational campaigns will extend beyond December. International collaboration might pool more resources. The object will not have departed the solar system by then. At its current trajectory, it will take years to recede beyond Saturn's orbit, while it will be exceedingly faint by that point. If the stakes are deemed sufficiently high, and if there is a genuine suspicion of artificiality, the investment in sustained monitoring would become justifiable. The forthcoming months represent a countdown not only to perihelion and Earth's closest approach, but also to a critical juncture in our understanding of interstellar space. Are we unique in creating technology capable of traversing the stars? Or are there other civilizations in our galaxy that dispatch their emissaries, intentionally or inadvertently, into neighboring solar systems? 3 Atlas may provide an answer to this question, or it may leave us with ambiguous data and conflicting interpretations. Regardless, time is of the essence, and by the time of the winter solstice, our knowledge will have significantly advanced from its current state. Part 6 delves into observational systematics and projection pitfalls. It's important to recognize that not every unusual celestial phenomenon is inherently strange. Often, what appears extraordinary is merely ordinary physics observed from an unconventional perspective. This is a fundamental principle of observational astronomy, consistently learned and relearned over centuries. The apparent backward motion of Mars perplexed ancient astronomers until the heliocentric model elucidated it as a consequence of perspective. The so-called canals of Mars were ultimately revealed to be optical illusions, where the human eye perceived patterns in random features. Similarly, many comets have appeared to invert their tails, when in reality, only our viewing angle had shifted. The core question confronting 3 Atlas is whether we are witnessing an intrinsic reversal of jet activity or a perceived effect due to projection. The distinction is of immense importance. An intrinsic reversal necessitates a physical explanation, indicating a change occurring within or on the comet itself. A projection effect, on the other hand, is purely a matter of geometry, stemming from Earth's motion relative to the comet, which creates an apparent reversal while the actual ejection pattern remains constant. To elaborate on how projection effects operate, a comet expels material in three-dimensional space, but our observation is a two-dimensional projection onto the celestial sphere. Our line of sight collapses depth information, making it challenging to differentiate between material moving towards us, away from us, or perpendicular to our view. As Earth traverses its orbit around the Sun and the comet follows its own trajectory, the geometry of observation is continuously altered. What initially seemed to be directed in one manner can appear to reverse as our vantage point shifts. A classic illustration of this is the anti-tail phenomenon, recognized for over a century. When Earth crosses a comet's orbital plane, dust particles trailing behind the nucleus along its orbit appear to point towards the Sun, creating an anti-tail. This occurs because we are viewing the dust trail from its edge. The particles are not actively moving towards the Sun, but are trailing the comet along its path. However, from our temporary viewing angle, they project as a forward-pointing feature. Subsequently, as Earth continues its orbital journey, exiting the comet's orbital plane, the anti-tail dissipates, and the conventional tail becomes prominent once more. Astronomers employ sophisticated methodologies to distinguish between genuine and apparent changes. Vector tomography, for example, utilizes observations from multiple dates and vantage points to reconstruct the three-dimensional distribution of material. By observing the comet from a sufficient number of diverse perspectives, one can reverse engineer the problem to determine the actual spatial structure responsible for the observed two-dimensional projections. This technique is most effective when the viewing geometry undergoes significant variation, providing ample angles for triangulation. Polarimetry offers another diagnostic tool. Dust particles scatter sunlight, and this scattering results in polarization. The degree and direction of polarization are contingent upon the scattering angle, which is the angle formed by incoming sunlight, the dust particle, and our line of sight. Different viewing geometries produce distinct polarization signatures, even if the dust distribution remains unchanged. By measuring polarization over time, it is possible to ascertain whether observed morphological changes are consistent with static dust, illuminated from varying angles, or if they necessitate an actual redistribution of material. Time-sequenced imaging also proves beneficial. If images are captured with sufficient frequency, one can observe the evolution of individual features, tracking their movement across the sky and in relation to the nucleus. Features that are genuinely new, representing actual changes in emission patterns, will emerge and develop in ways that are inconsistent with the simple projection of static structures. Features that are projection artifacts will shift predictably as the viewing geometry changes, following mathematical models of perspective transformation. Historical instances inform this analysis. Comet Arend-Roland in 1957 exhibited a striking anti-tail as Earth crossed its orbital plane. Observers were initially astonished by this sunward-pointing spike, with some speculating about unusual physical processes. Careful geometric analysis revealed it to be entirely a projection effect, with dust distributed along the comet's orbit appearing to point forward due to the viewing angle. More recently, Comet Lulin in 2009 displayed anti-tail features that were similarly resolved as geometric effects. Now, let us apply these lessons to 3 Atlas. Between July and September, Earth's position relative to the comet underwent significant alteration. Both celestial bodies were in motion. Earth in its nearly circular orbit and 3 Atlas on its hyperbolic trajectory towards the Sun. the geometric configuration shifted, affecting phase angles, scattering angles, and the projection of any three-dimensional structures within the coma onto the two-dimensional sky. The team at the Nordic Optical Telescope, which tracked the comet during this period, would have been cognizant of projection pitfalls. Their analysis presumably incorporated geometric modeling to ascertain whether the observed changes could be attributed solely to Earth's changing position. The fact that they reported an intrinsic jet reversal suggests that their models ruled out purely projection-based effects. However, such exclusions rely on assumptions regarding dust distribution, ejection velocities, and other parameters. Uncertainty in these assumptions leaves room for alternative geometric explanations. One method to test this is through simulation. A model comet with static dust ejection, featuring a fixed pattern of jets or isotropic outgassing, can be generated. Researchers can then calculate what Earth-based observers would perceive on different dates as the viewing geometry evolves. These predictions can then be compared to actual observations. A close match suggests that projection effects are dominant. Conversely, if the predictions fail to replicate the observed features, intrinsic changes become necessary. The challenge lies in the fact that real comets are not static. Even if the jet reversal is a projection effect, the comet itself is still undergoing changes. Outgassing rates fluctuate as the heliocentric distance decreases, dust production varies, and active regions may switch on or off. Rotation also brings different surface areas into and out of sunlight. Differentiating between the influence of viewing geometry and genuine activity changes requires meticulous modeling of both aspects. Polarimetric data, if available, would significantly aid this endeavor. Reports have not specified whether polar imagery of 3I Atlas was acquired during the critical July to September period. If such data exist, they could provide constraints on dust grain properties and scattering geometry, thereby narrowing the possibilities between projection and intrinsic interpretations. If polarimetry was not performed, this represents a gap that future observations might potentially fill, although by then, the geometric configuration will have changed once more. Another factor to consider is the abruptness of the observed transition. Projection effects tend to be smooth and gradual as the viewing geometry evolves incrementally. A sudden reversal occurring over a few days, rather than weeks, would suggest an intrinsic phenomenon. However, defining sudden versus gradual is subjective, particularly when the observation cadence is irregular. If imaging occurs weekly, a change that transpired over 3 days might appear sudden, whereas the same change, sampled daily, could seem more gradual. The corroboration from multiple independent observers strengthens the evidence. If several telescopes at different locations, employing different instruments and under varying observational conditions, all report the same transition, the likelihood of instrumental or observational artifacts diminishes. The Nordic Optical Telescope, the Hubble Space Telescope, and potentially other facilities constitute a network for cross-checking. Consistency across these platforms argues for the reality of the phenomenon over mere artifact. The compositional aspect also warrants consideration. Projection effects cannot alter spectral signatures. If the chemistry of the emitted materials shifted between July and September, this would be an intrinsic change, not a geometric one. Spectroscopic follow-up observations reportedly detected compositional changes that support the physical transition model. However, the specifics are critical. How robust were the spectral features? What uncertainties are associated with these measurements? Were multiple wavelengths observed, providing reliable compositional diagnostics? The risk of confirmation bias looms. Once researchers develop a belief that they have discovered something unusual, they may interpret ambiguous data in a manner that supports this preconceived notion. Independent analysis by teams without a vested interest in the outcome serves as a valuable check. Have skeptical investigators examined the data? Are there alternative explanations that have not been fully explored? The scientific process inherently involves adversarial collaboration, wherein different groups challenge each other's interpretations, thereby demanding more robust evidence and more compelling arguments. When all these factors are taken into account, viewing geometry, dust dynamics, instrumental effects, observational cadence, one realizes the difficulty in asserting absolute certainty. The honest assessment is that projection effects likely do not account for the entirety of the observed reversal, but they may contribute. The interpretation of an intrinsic jet flip is probably accurate, yet it is accompanied by acknowledged uncertainties. And these uncertainties are significant when determining the level of exoticness to ascribe to the explanation. Part 7 examines the dynamics of small versus large particles and the sorting of dust sizes. Dust grains are not uniform, and their variations dictate much of what we observe when studying comets. The physics governing these microscopic particles, fragments of rock and ice ranging in size from nanometers to millimeters, explains why comet tails stream away from the sun, why some comets appear dusty while others seem gas-rich, and potentially why 3 Atlas initially displayed sunward emission before its tail reversed. Let us begin with the beta parameter, a dimensionless quantity representing the ratio of solar radiation pressure to solar gravity acting on a dust grain. Small particles exhibit a high beta value, meaning sunlight exerts a stronger outward push than gravity's inward pull. Conversely, large particles have a low beta value, experiencing gravity more intensely relative to light pressure. The crossover point occurs at approximately micron scales, with precise values dependent on composition, shape, and distance from the sun. For extremely small grains, those less than a micron in size, beta can exceed 1. This implies that radiation pressure overwhelms solar gravity. Once released from the comet, these particles accelerate away from the sun at a rate exceeding their inward fall. They form the classic comet tail, a luminous streamer extending millions of kilometers anti-sunward. The smaller the grain, the greater its acceleration, and the straighter its tail appears. Larger grains with a beta value less than 1 follow more curved trajectories, representing a balance between their orbital motion and the outward push of sunlight. Now, consider the behavior of grains with very low beta values, particles tens or hundreds of microns in diameter. These grains are minimally affected by radiation pressure. They are expelled from the comet with a certain initial velocity, driven by the sublimation of gas, but subsequently follow nearly ballistic trajectories dictated by their orbital path around the sun. These particles form dust trails, extended structures that trace the comet's orbit, often lagging behind the nucleus because they were released at an earlier point when the comet was at a different position in its path. Under specific geometric conditions, these large, low-beta grains can appear to point towards the sun. If Earth's viewing angle aligns favorably, the trailing dust distributed along the comet's orbit behind its current position projects as a forward-pointing feature. This is the underlying mechanism of classical anti-tails and requires no actual sun-facing emission. It is purely geometric. The relevant equations describe grain drift. A particle released from the comet with a given velocity and beta value will follow a perturbed orbit. Its trajectory can be calculated by integrating the equations of motion, incorporating solar gravity and radiation pressure as vector forces. The outcome depends on the release position, release velocity, and beta value. By summing the trajectories of numerous grains with varying sizes and release times, one can construct a predicted 3-dimensional distribution of dust. Subsequently, researchers predict what Earth-based observers will perceive by projecting this distribution onto the celestial sphere. This forward modeling approach allows for hypothesis testing. If one assumes the comet releases dust isotropically with a specific velocity and grain size distribution, one can then predict brightness patterns and compare them to observed data. a good match validates the assumptions, while discrepancies indicate an issue with the dust properties or ejection pattern. For 3 Atlas, the critical question is whether the observed sunward glow in July could be attributed to low beta dust within an anti-tail configuration. The answer hinges on several factors. Firstly, the comet's orbital plane and the viewing geometry. Secondly, the grain size distribution. If the majority of the dust consists of small, high beta material, a pronounced anti-tail will not form, even with advantageous geometry. However, if a significant fraction comprises large, low beta grains, an anti-tail becomes plausible. Thirdly, the grain lifetime. While larger particles may persist for longer durations, they will eventually fragment or sublimate under intense solar heating. The survival time is contingent on composition. Ice-rich grains sublimate relatively rapidly, with lifetimes measured in hours to days at a distance of 1 astronomical unit from the Sun. Refractory grains, rocky particles with minimal volatile content, survive for extended periods, potentially weeks or months. If 3 Atlas released refractory dust early in its approach, these particles might still be present, forming a trail that projects as an anti-tail when viewed edge-on. Ejection velocity is also a significant factor. Gas drag, resulting from sublimation, propels dust away from the nucleus, but the terminal velocity depends on grain size and the rate of gas production. Small grains can reach velocities of hundreds of meters per second, while large grains might only achieve tens of meters per second. Lower ejection velocities mean that grains remain closer to the comet's orbit, increasing the geometric probability of anti-tail projections. Certain thresholds must be considered. Grains larger than approximately 50 microns, released with velocities below about 100 meters per second, at heliocentric distances of 2 to 3 astronomical units, could produce sunward enhancements under appropriate viewing angles. However, such enhancements would be relatively faint, as large grains scatter less light per unit mass compared to smaller grains. A substantial mass of dust in large particles would be necessary to create the bright anti-tail observed in Hubble's July image. The Loeb and Keto model proposes that initial sunward emission was due to small, ice-coated grains rather than large refractory ones. Their argument suggests that the sublimation of carbon dioxide early in the approach released ice grains that, when viewed from Earth's geometric perspective, forward-scattered sunlight effectively. These grains, being small, possessed high beta values and short lifetimes, forming a compact, luminous feature that appeared sunward not due to projection, but because of actual preferential emission, combined with their scattering properties. This interpretation shifts the explanation from orbital dust trails to active emission patterns. The grains are not trailing from previous epochs. They are being produced recently, with characteristics and velocities that, in conjunction with the viewing geometry, create a forward-scattered glow. As the comet transitioned to water and refractory dust, the grain population changed. Larger, darker particles replaced the bright ice grains, diminishing the forward scattering while enhancing the classical backscattering from tails composed of larger grains, thus accounting for the observed reversal. Uncertainties abound. The precise grain size distribution of 3 Atlas remains unknown. Observational data provides some constraints through measurements of brightness and color, but degeneracies exist. A particular brightness level could result from a multitude of small grains, or a lesser quantity of large grains. The spectral slope, which describes how brightness varies with wavelength, offers clues, but its interpretation necessitates assumptions about composition and shape. Anisotropic ejection further complicates matters. If jets are concentrated rather than uniform, the dust distribution becomes directional. Different viewing angles will encounter varying amounts of dust, even if the total production rate remains constant. Rotation further modulates this distribution. As the celestial body rotates, Its ejected streams diverge in numerous directions, generating emissions that fluctuate over time and interact with observational geometry in intricate ways. The theory of dust particle size segregation naturally accounts for certain anti-tail phenomena. While this is plausible, the magnitude and timing of the reversal observed with 3I Atlas challenge the limits of explanations relying solely on geometric factors and particle size distributions. The suddenness, stark differences in brightness, and shifts in spectral characteristics all indicate more than just passive dust trailing or projection illusions. Something fundamentally altered the nature and composition of the comet's output. Although the physics of dust contributes to understanding this transformation, it likely falls short of a complete explanation without considering changes in composition or other intrinsic evolutionary processes, which is significant for the broader interpretation. If dust size sorting and projection effects were sufficient to explain all observations, the hypothesis of an artificial construct would be rendered unnecessary. Well understood, albeit complex, natural cometary behavior would suffice. However, if these geometric explanations prove inadequate, leaving residual anomalies after accounting for dust dynamics, then more unconventional possibilities remain viable. The physics of dust constrains the range of potential explanations, but does not yet definitively identify the correct one. Part 8 concerns instrument and analysis cross-checks. Telescopes can be deceptive, or at least misleading, if not used with caution. Every instrument possesses inherent biases, artifacts, and systematic errors that can falsely appear as genuine celestial phenomena. This underscores why astronomers prioritize cross-verification, comparing observations from diverse telescopes equipped with different instruments, conducted under varying conditions. When multiple independent systems corroborate a finding, confidence in its reality increases. Conversely, discrepancies suggest either a malfunctioning detector or an analytical error. The collection of observatories that contributed data on 3I Atlas encompasses both ground-based and space-based facilities. The Hubble Space Telescope, humanity's foremost optical observatory, captured the pivotal July 21st image, revealing the sunward-facing anti-tail. Hubble's wide field Camera 3 provides exceptional spatial resolution and meticulously calibrated photometry. It has been operational for over a decade, imaging thousands of celestial targets with well-established performance characteristics. The Nordic Optical Telescope, a 2.5-meter ground-based instrument situated in La Palma, provided the observational sequence from July through September that documented the tail's evolution. Ground-based telescopes contend with environmental challenges, unlike their space-based counterparts. Atmospheric turbulence, meteorological conditions, and daylight limitations present obstacles. Yet ground telescopes offer flexibility, swift response capabilities, and continuous accessibility, unmatched by often oversubscribed space facilities. The Nordic Optical Telescope has a long history of cometary observations, with experienced teams adept at extracting signals from faint, moving targets. Other facilities likely also contributed. The KEK Observatory in Hawaii, with its twin 10-meter telescopes, possesses the capacity for high-resolution spectroscopy of faint objects. Gemini South in Chile offers comparable capabilities in the southern hemisphere. These large aperture instruments can collect sufficient light from a comet's coma to disperse it into spectra, revealing compositional details through the emission lines of specific molecules. Mars orbiters represent a distinct category of observer. The Mars Reconnaissance Orbiter's high-resolution imaging science experiment, HiRISE camera, designed for imaging the Martian surface at sub-meter resolution, has occasionally been repurposed to observe comets passing near the red planet. If 3I Atlas was observable from Mars during the October 3rd flyby, HiRISE could have captured images from a perspective vastly different from that of Earth-based telescopes. This diversity of viewpoints aids in resolving ambiguities when interpreting three-dimensional structures from two-dimensional projections. The James Webb Space Telescope, despite requiring advanced scheduling, may have allocated observation time to 3I Atlas. JWST's near-to-mid-infrared spectroscopy excels at detecting water, carbon dioxide, carbon monoxide, and organic molecules within cometary envelopes. Observations conducted at wavelengths where ice and dust exhibit distinct spectral signatures would offer more precise compositional constraints than optical data alone. Each instrument presents unique challenges. While Hubble's pointing stability is excellent, tracking rapidly moving solar system objects necessitates meticulous planning. The telescope must adjust its aim to follow the target during an exposure, compensating for the object's movement against the backdrop of stars. Imperfect tracking can lead to trailing or smearing, elongating the image in the direction of movement. This elongation could potentially obscure or be mistaken for genuine morphological features such as jets or tails. Ground-based telescopes are subject to atmospheric seeing, the blurring effect caused by atmospheric turbulence. Adaptive optics systems offer partial compensation by employing deformable mirrors to correct wavefront distortions in real time, though this correction is not entirely flawless. Residual seeing can soften fine details, making sharp jets appear diffuse. Weather patterns introduce interruptions in data acquisition. Clouds, wind, and poor atmospheric transparency all restrict observing windows. A crucial brightening event or morphological alteration occurring during unfavorable weather conditions would go unrecorded. Photometric calibration demands precision. Accurately measuring brightness requires determining the total amount of light entering the telescope, while correcting for atmospheric extinction, instrument throughput, and detector efficiency. Different telescopes employ distinct calibration methodologies. Systematic discrepancies of 10 or 20% are common, particularly for faint, extended objects like comets, where choices in aperture selection and background subtraction significantly influence measured brightness. Background subtraction presents a particular challenge with comets. The coma, a diffuse envelope of gas and dust, lacks a distinct boundary. Defining the point at which the comet ends and the sky begins is inherently subjective. Positioning the background annulus too close risks incorporating coma light, leading to an underestimation of the comet's brightness. Placing it too far might encompass background stars or galaxies, inflating the background measurement and consequently boosting the comet's reported brightness. Variations in observer judgment introduce scatter into photometric results. Spectroscopy adds another layer of complexity. Extracting a spectrum from a faint, extended source necessitates careful attention to slit placement, orientation, and width. The slit should ideally align with noteworthy features, perhaps a jet's axis, to maximize signal capture. However, the comet is in motion, and its morphology may be undergoing changes. A spectrum obtained on one night might sample a different region than one acquired a week later, rendering direct comparisons problematic. Wavelength calibration in spectroscopy utilizes lamp spectra with known emission lines. Minor calibration errors, even a fraction of an angstrom, can shift the perceived location of a spectral feature, leading to misidentification of molecules. Fluctuations in temperature and pressure within the instrument can induce drifts between calibration and science exposures. Vigilance and redundant calibrations help mitigate these issues, but do not eliminate them entirely. Cross-comparison between different telescopes serves to identify systematic errors. If both Hubble and another observatory observe the sun-facing anti-tail in July, this feature can be considered real, rather than an artifact of a single instrument. Similarly, If spectroscopy from KEK and Gemini both detect carbon dioxide emission, the molecular identification gains significant confidence. Consistency across multiple platforms argues against instrumental artifacts as the explanation for observed features. Though perfect consistency is rare, observers frequently report discrepancies, including variations in measured brightness and minor morphological differences. Some of these variations represent genuine, real-time variability, as comets can change on timescales of hours to days. Others are instrumental in origin. Disentangling these requires sophisticated modeling. This involves simulating observations from each instrument, accounting for factors like resolution, sensitivity, tracking inaccuracies, and atmospheric seeing. These simulations are then compared to the actual data. Any remaining differences highlight phenomena not explained by known instrumental effects. The multi-filter approach assists in addressing wavelength-dependent characteristics. Optical images captured through blue, green, and red filters probe different segments of the spectrum. Dust and gas exhibit distinct color properties. Dust scatters sunlight appearing white or slightly reddened, while gas emissions manifest as discrete spectral lines, shining brightly in specific filters depending on the active transitions. Comparing brightness across these filters helps distinguish between dust and gas, thereby constraining composition and activity levels. Infrared observations complement optical data. Water and carbon dioxide possess strong absorption bands in the near-infrared spectrum. The James Webb Space Telescope or ground-based infrared instruments can measure flux within these bands, directly quantifying volatile abundances. Thermal emission at mid-infrared wavelengths reveals the nucleus's temperature, which informs models of subsurface heat conduction and sublimation rates. If conducted, polarimetry provides orthogonal information. Dust grains scatter light anisotropically, producing a net polarization that is contingent upon the scattering angle and grain properties. Measuring polarization across multiple wavelengths and observation dates constrains grain size, shape, and composition independently of brightness measurements, especially when combined with photometry and spectroscopy. Polarimetry effectively narrows the parameter space, reducing ambiguities. The question persists whether instrumental and analytical systematics could fabricate the observed jet reversal. The answer is almost certainly no. No plausible combination of tracking errors, calibration mistakes, or background subtraction choices could create a spurious sun-facing feature in July that subsequently vanishes, while an anti-solar tail emerges in September. Such consistent, multi-observatory, multi-epoch signatures necessitate a physical explanation rooted in the comet's behavior, not instrumental artifacts. Nevertheless, quantitative precision is crucial. The exact brightness of the anti-tail, the speed at which the transition occurred, and the strengths of spectral lines are all vital. These numerical values, along with their associated error bars, determine which models align with the data and which do not. If instrumental uncertainties are greater than anticipated, the range of possible explanations broadens, allowing more hypotheses to remain viable. Conversely, if uncertainties are smaller, the constraints tighten, potentially ruling out certain possibilities. Follow-up observations conducted after perihelion will continue to test these hypotheses. High-cadence monitoring images, acquired every few days, capture transient events and precisely track brightness evolution. Multi-wavelength coverage, spanning the ultraviolet to the infrared spectrum, constructs a comprehensive picture of composition and thermal state. Polarimetry adds further constraints on grain properties. Radio observations, though technically challenging for such a faint target, might detect molecular line emission, offering additional compositional diagnostics. The collaborative effort of the global astronomical community, with multiple observatories targeting the same object using complementary techniques, represents modern astronomy at its finest. No single instrument can provide the complete narrative, but collectively, when cross-checked and calibrated, they build a data set robust enough to differentiate between genuine phenomena and artifacts, and between natural occurrences and extraordinary events. Part 9 examines the sociology of a controversial object and the influence of prominent figures. Science is conducted by humans, and humans bring their full complexity to this endeavor, including egos, ambitions, reputations, career pressures, and the desire to be the first, to be correct, or to achieve fame. We tend to believe that scientific truth emerges purely from data and logic, but the process is often more convoluted. This is particularly true when a renowned scientist anchors their reputation on a controversial concept. This is precisely the situation with 3I Atlas. Abraham Loeb is not an ordinary astronomer. He is the former chair of Harvard's astronomy department, a prolific author, and a public intellectual who engages with the media with an enthusiasm most academics eschew. He is known for formulating bold hypotheses and for his willingness to consider ideas that his peers might dismiss as excessively speculative. Oumuamua, the first confirmed interstellar visitor in 2017, became a focal point for Loeb's advocacy of technosignatures. He proposed it might be a light sail, an artificial structure propelled by radiation pressure, whereas most astronomers favored natural explanations, such as exotic ice or unusual cometary activity. The Oumuamua incident polarized the scientific community. Some appreciated Loeb's readiness to think beyond conventional boundaries, his advocacy for seriously considering technosignatures, and his efforts to draw attention and funding to SETI research. Others recoiled at what they perceived as premature speculation, arguing that proposing alien artifacts without compelling evidence undermines scientific credibility and makes the field appear frivolous to funding agencies and the public. Now, 3I Atlas has become the next arena of contention. Loeb and his collaborators have published and spoken about the possibility of controlled movement, suggesting the object could be a probe executing maneuvers. The media, predictably, amplified this aspect. Following Science's publication of articles highlighting the engineered object hypothesis, mainstream news outlets seized upon the story. Suddenly, headlines began referring to 3I Atlas as potentially artificial, despite a strong scientific consensus favoring natural explanations. This phenomenon is known as the Loeb effect. His prominence, media connections, and rhetorical skill attract disproportionate attention to hypotheses that, if proposed by less visible scientists, might circulate quietly among specialists. This attention carries both advantages and disadvantages. On the positive side, more people become aware of interstellar objects. Funding agencies take notice. Telescope time allocation committees might dedicate resources for follow-up studies. Public engagement with astronomy increases, potentially inspiring future generations of researchers. On the downside, sensationalized framing can be misleading. If the public comes to believe that 3I Atlas is likely artificial, and later data confirm its natural origin, trust in astronomical expertise may erode. Why should the public trust scientists if they repeatedly suggest alien origins only to retract those claims later? The damage is compounded if Loeb is perceived as representative of astronomers in general, when in fact he is an outlier in his eagerness to publicize speculative ideas. The scientific community grapples with how to address provocative assertions. Peer review is designed to filter out weak ideas before publication, but the threshold for publication differs from the threshold for widespread acceptance. Papers proposing Oumuamua as artificial passed peer review and were published in respected journals, yet most astronomers did not find them convincing. This is a normal part of the scientific process. Science thrives on disagreement. However, when disagreements enter the public sphere, non-experts struggle to assess their validity. The question of motive also arises. Critics suggest Loeb's advocacy is partly driven by self-promotion, book sales, and the maintenance of a public profile that yields speaking fees and consulting opportunities. Defenders, however, counter that ad hominem attacks do not address the scientific arguments. Whether Loeb benefits personally is irrelevant if his hypotheses are testable and his analyses are sound. One should judge the ideas, not the person. Yet, motive can subtly influence the process. If a scientist is motivated to make bold claims, they might interpret ambiguous data optimistically, perceiving signals where skeptics discern noise. Confirmation bias, the tendency to favor information that supports pre-existing beliefs, affects everyone, but is intensified when one's reputation is at stake. Loeb has cultivated a brand centered on techno-signature advocacy. Backtracking on claims or admitting error would damage that brand. This creates pressure, whether conscious or not, to defend hypotheses, even as contradictory evidence mounts. The media ecosystem amplifies everything. A measured scientific paper titled, for example, Potential Compositional Transition in 3I Atlas, can become a headline proclaiming, "Scientists believe new comet could be alien spacecraft." Context is lost, and caveats disappear. The nuanced debate among experts is reduced to a binary choice, alien or not. This simplification does a disservice to the scientific process, which rarely deals in absolutes, particularly concerning unusual observations of distant objects. Funding politics also plays a role. SETI research has historically struggled to secure adequate support. Mainstream funding agencies are hesitant to invest in searches that may never yield definitive results. However, high-profile cases like Oumuamua or 3I Atlas generate significant public interest. If Loeb's advocacy helps secure funding for techno-signature searches, then perhaps the cost in terms of reputational risk is justifiable. It is arguably better to have people debating the artificiality of this comet than to ignore interstellar visitors entirely. Some colleagues express concern about setting precedents. If every unusual astronomical object prompts speculation about artificiality, the signal-to-noise ratio in our understanding will plummet. We have discovered thousands of exoplanets, observed countless transient events, and cataloged millions of galaxies. Anomalies are commonplace within this vast data set, and most resolve to natural explanations once more precise data become available. If we prematurely cry alien every time an observation deviates from established models, we diminish the significance of genuinely anomalous findings. Others argue that this approach is precisely the point. We should be actively searching unusual objects for techno-signatures. The cost of false positives, expending effort on natural objects briefly considered artificial, is low compared to the cost of false negatives, missing actual alien technology due to insufficient investigation. This asymmetry favors a liberal approach to hypothesis testing. Furthermore, there's the question of epistemic protocol, how the scientific community should handle speculative claims. One approach involves gatekeeping, regulating discourse to prevent premature speculation from reaching the public. However, gatekeeping has its drawbacks. It can stifle creativity, discourage unconventional thinking, and perpetuate groupthink, where individuals fear proposing ideas outside the mainstream. The opposing approach is radical openness, allowing all ideas to compete in a marketplace where data and argument determine their validity. While this sounds democratic, it risks confusion when non-experts are unable to evaluate competing claims. A middle path involves meta-communication. When proposing speculative ideas, clearly label them as such, quantify probabilities, and explain what observations would serve to falsify the hypothesis. Acknowledge alternative, mainstream explanations. This makes it easier for audiences, both specialists and the general public, to understand the epistemic standing of the claims being made. Loeb and his collaborators sometimes engage in this careful approach, noting that natural explanations are favored. However, the framing in media appearances can be less cautious. The upcoming months will serve as a real-time test of the Loeb effect. If 3-Eye Atlas ultimately proves to be natural, Loeb's critics will argue that this demonstrates his excessive eagerness to invoke alien origins. His defenders will contend that he advanced testable hypotheses and followed the data wherever it led. If anomalies persist and the engineered object hypothesis gains traction, Loeb will be vindicated, and his early speculations will be seen as prescient. Regardless of the outcome, this episode will inform future approaches to handling similarly controversial objects. What remains certain is that science is a social process. Data do not interpret themselves. Humans decide which observations to conduct, which models to test, and which hypotheses warrant resources. These decisions reflect not only logic and evidence, but also career incentives, disciplinary norms, and the personalities of key individuals. 3-Eye Atlas, irrespective of its true nature, has become a lens through which to view the actual workings of science, with all its complexities, political dimensions, and human drama. This narrative is as important to understand as the scientific findings themselves, because comprehending how we acquire knowledge is as crucial as knowing what we know. Part 10 delves into what the detection of artificiality would truly signify. Let us imagine, for a brief moment, that the improbable occurs. Picture a scenario months from now, after all the data have been analyzed, after every plausible natural explanation has been rigorously tested and found wanting, and the scientific community reaches a consensus. 3-Eye Atlas is not a comet. It is something else, something fabricated. What would it take to arrive at such a conclusion? The evidentiary standard must be extraordinarily high because the claim itself is exceptional. One would require multiple independent lines of evidence, each compelling on its own and collectively overwhelming. This would begin with sustained non-gravitational acceleration that cannot be explained by sublimation models. It's not merely minor orbital discrepancies within the margin of error, but evident, systematic deviations that indicate the celestial body is accelerating in ways not explainable by natural outgassing. The acceleration would also need to persist for an undue duration. Cometary bodies cease their outgassing when they journey far from the sun and cool down. If the object designated 3-Eye Atlas continued to exhibit propulsive forces long after thermal models suggested its volatile components should be dormant, that would certainly be a cause for suspicion. Furthermore, if the thrust appeared to engage and disengage intermittently, manifesting as discrete bursts rather than continuous sublimation, such a pattern would demand a compelling explanation. Repeatable alterations in the orientation of its ejection axes are also significant. Should the object have reoriented its emission direction multiple times, with each instance uncorrelated with solar heating or its rotational state, one would be compelled to question what mechanism governs that directional control. Naturally occurring comets exhibit jets that are intrinsically linked to active regions on their nuclei. These regions remain fixed in relation to the body's surface. As the object rotates, these jets sweep around, producing predictable patterns. Arbitrary reorientations that are disconnected from its rotational state would strongly suggest an external influence. Spectral anomalies would be particularly damning. If spectroscopic analysis revealed emission lines indicative of metallic elements, unusual molecular species, or patterns inconsistent with typical cometary volatiles, that would serve as a clear warning sign. Comets are fundamentally composed of ices and dust, remnants from the primordial solar system. They should not contain manufactured compounds or processed metals. The detection of such materials would necessitate extraordinary explanations, with artificiality being a primary consideration. Radio or radar signatures could prove instrumental. An artificially constructed object might intentionally emit electromagnetic radiation as a beacon, or unintentionally due to its internal systems. radio telescopes have been employed to monitor various anomalous celestial bodies over the years, typically yielding no significant findings. However, if 3I Atlas were to emit narrowband radio signals, exhibiting modulation patterns that deviate from natural phenomena, that would be an extraordinary development. Even thermal radio emission displaying an unexpected spectrum could allude to internal heat sources beyond mere solar warming. Then there is the analysis of its trajectory. Is its orbit unusual? Does it appear to be deliberately engineered? Interstellar objects typically arrive from random directions with velocities determined by their journeys through the galaxy. Conversely, an engineered probe might intentionally target the inner solar system, selecting a trajectory designed to maximize observation time or to test specific environmental conditions. Statistical arguments in this context are inherently weak due to the limited number of interstellar visitors we have encountered for comparison. Nevertheless, if the path of 3I Atlas displayed characteristics that seemed excessively convenient or too precisely tuned for a close solar approach, especially in conjunction with its proximity to Earth, suspicions would undoubtedly escalate. The confluence of these factors holds more weight than any single observation in isolation. A single anomaly can often be rationalized away. Perhaps the observed acceleration is simply a result of asymmetric outgassing that we do not yet fully comprehend. Perhaps a spectral feature is attributable to contamination or a misidentification. However, when one accumulates evidence of acceleration, coupled with spectral anomalies, radio emissions, and trajectory fine-tuning, natural explanations begin to falter. At a certain threshold, attributing the phenomenon to multiple improbable coincidences becomes a less parsimonious explanation than accepting the simpler hypothesis that the object is artificial. Verification protocols would need to be exceptionally stringent. The SETI community has, in fact, deliberated on procedures for confirming techno-signatures. Independent observatories would be required to replicate any findings. Multiple analysis teams should scrutinize the data independently, meticulously checking for errors or alternative interpretations. The statistical significance must surpass 5 sigma, the established benchmark for major discoveries in the field of physics. Peer review must be conducted in an open and adversarial manner, with skeptics granted unrestricted access to all data and methodologies. The geopolitical ramifications would be immediate. Who would claim ownership of such a discovery? Which nation or institution would receive attribution? Would artificial imply current technological capabilities, or an ancient artifact? If it were a probe dispatched by an active civilization, are they currently observing us? Should we attempt to establish communication? These inquiries transcend the realm of pure science, extending into the domains of diplomacy, security, and philosophy. The United Nations possesses an office dedicated to outer space affairs, which theoretically oversees international responses to such scenarios. However, no concrete protocol has ever been tested for an artificial object entering our solar system. Would governments opt for information classification, fearing public panic, or seeking a military advantage? Or would transparency prevail with data disseminated openly? The response might well hinge on the object's behavior, specifically whether it appears passive or reactive. Mission concepts designed to intercept 3I Atlas would face formidable constraints. The object is moving at high speed along a hyperbolic trajectory. Following its closest approach to the Sun, it will be rapidly receding from the solar system at immense velocity. Intercepting it necessitates a spacecraft capable of achieving enormous delta V, the alteration in velocity required to match trajectories. Conventional chemical rockets are insufficient for this task with reasonable payload mass. Nuclear propulsion might offer a solution, but it is not yet ready for flight. Solar or laser sails could gradually increase speed over time, but are unlikely to achieve the necessary velocity to intercept 3 Atlas before it departs the accessible regions of the solar system. proponents have put forth fast flyby mission concepts. These involve launching small probes on trajectories optimized for minimum transit time, aiming to intercept the object while it remains within a few astronomical units of the Sun. These missions would not involve rendezvous, but rather a rapid pass at high relative velocity, capturing images and spectral data during a brief encounter lasting mere minutes or seconds. Even such a limited mission would demand expedited development, launch within several months, and substantial financial investment. The likelihood of approval through conventional channels is effectively nil. Alternative strategies involve prolonged observation rather than physical interception. This would entail continuing to track 3I Atlas for years as it recedes, monitoring for any changes in its behavior, radio emissions, or trajectory adjustments. It might also involve deploying new observational assets, such as dedicated space telescopes, specifically engineered for tracking faint objects in the outer solar system. While the data may never offer definitive proof, the gradual accumulation of evidence over an extended period could sufficiently alter probabilities to inform future decisions. Should artificiality be confirmed, the implications would cascade across every conceivable domain. Firstly, the profound realization that humanity is not alone. This has been a lingering suspicion, even an assumption for many scientists given the vastness and age of the universe. However, knowledge surpasses mere suspicion. Definitive proof of extraterrestrial technology would represent the most significant discovery in human history, fundamentally reshaping philosophy, religion, science, and our perception of cosmic significance. Secondly, it would demonstrate the feasibility of interstellar travel. If a civilization has successfully dispatched a probe across light years, then the engineering challenges we currently deem nearly insurmountable have evidently been overcome. This suggests that civilizations can endure for sufficient periods to develop such advanced capabilities. This would provide a crucial data point for the Drake equation, which estimates the number of technological civilizations present in our galaxy. It also implies that the galaxy may be replete with such probes, forming a network of exploration established by multiple species. Thirdly, we would be compelled to reevaluate previous anomalies. Was the object Oumuamua artificial as well? Are there other objects within our astronomical catalogs that we have dismissed as natural, but which warrant re-examination? How many interstellar visitors have traversed our solar system undetected simply because we were not actively searching for them? Such a discovery would undoubtedly trigger an extensive period of retrospective analysis, involving a thorough examination of archival data for overlooked patterns. Fourthly, there are profound implications for humanity's future. If other civilizations have achieved interstellar capability, then it is conceivable that we might too. The prospect of star travel would transition from speculative conjecture to a concrete engineering challenge. Funding and prioritization for such endeavors could experience a significant shift. Perhaps we are witnessing the navigational markers left by ancient civilizations, and our own destiny is to join that cosmic community. Alternatively, we might be observing the remnants of extinct societies, serving as a stark warning about the formidable challenges that lie ahead. The null hypothesis, asserting a natural origin, remains vastly more probable. 3 Atlas is almost certainly a natural comet, exhibiting unusual, but ultimately explicable behavior. The compositional transition model likely accounts for the majority, if not all, of the observed phenomena. The hypothesis of an engineered object will likely recede as further data become available, joining the extensive list of initially intriguing anomalies that ultimately resolve into mundane explanations. However, the exercise of contemplating the implications of artificiality is inherently valuable. It clarifies precisely what evidence would be necessary, which observations should be prioritized, what follow-up actions are sensible, and it underscores the inherent asymmetry of the situation. If the object proves to be natural, we will gain valuable insights into cometary science and move forward. If, however, it is artificial, everything changes. This inherent asymmetry justifies rigorous scrutiny. Even if the probability of an artificial origin is exceedingly small, the time frame for acquiring more definitive answers is rapidly diminishing. By December 19th, Earth's closest approach, a significantly clearer picture should emerge. Post-perihelion observations will have tracked the object for weeks under intense solar heating. Spectroscopic analysis will have characterized its composition. Astrometric measurements will have quantified any non-gravitational forces. The gathered data will converge towards a definitive answer, or leave us with frustrating ambiguity, necessitating long-term monitoring. Regardless of the outcome, 3 Atlas represents a crucial test case for how we approach and manage anomalous observations of interstellar visitors. The processes, the debates, and the observational strategies currently being developed will undoubtedly be applicable to future encounters with such objects. As survey telescopes like the Vera C. Rubin Observatory become operational, discovering interstellar visitors at an increased rate, robust protocols for rapid assessment, prioritization, and follow-up will become essential. 3 Atlas is, in essence, teaching us how to implement these protocols. Regardless of its ultimate nature, the spectrum of possibilities remains open. It could be a natural comet, an exotic natural object, or something genuinely artificial. The ensuing months will serve to narrow this range of possibilities, systematically excluding options as data accumulate. Whatever remains will represent the truth, irrespective of its nature. And that truth will undoubtedly constitute a narrative worth recounting, whether it confirms our existing understanding or fundamentally overturns it. Part 11. NASA reopens Artemis lander competition. While astronomers engage in discourse regarding the nature of celestial bodies originating from other star systems, closer to home, NASA is grappling with the complexities of returning humans to the moon. The Artemis program, named after the twin sister of Apollo in Greek mythology, aims to achieve lunar landings by astronauts for the first time since 1972. However, the path back to the moon has been fraught with challenges. Recent developments strikingly highlight the same underlying tensions between ambitious goals and cautious execution that characterize the investigation into 3I Atlas. In late 2025, NASA announced its decision to reopen the competition for the Artemis 3 lunar lander, moving beyond the initial sole contract awarded to SpaceX. That award, announced several years prior, designated SpaceX's Starship vehicle as the designated system responsible for transporting astronauts from lunar orbit to the surface. Starship, a colossal rocket still undergoing development, promises unprecedented capabilities, but has encountered repeated delays, technical hurdles, and the inherent unpredictability of cutting-edge engineering. The decision to reopen the competition reflects a confluence of practical considerations and political pressures. From a practical standpoint, relying on a single contractor for such a critical mission component introduces inherent risk. Should Starship development encounter insurmountable obstacles, the entire Artemis schedule would collapse. Securing a backup option, such as a second lander design from a different company, provides a crucial safety net. It also fosters competition, theoretically driving innovation and leading to more cost-effective solutions. Politically, distributing contracts among multiple companies ensures broader stakeholder satisfaction. Blue Origin, Jeff Bezos' prominent space venture, has been vocal in its pursuit of lunar lander work. Established aerospace contractors like Lockheed Martin and Northrop Grumman possess both the necessary capabilities and significant political influence. Opening the competition provides them with another opportunity to submit proposals and offer alternatives to Starship's ambitious design. The implications of this decision extend throughout the space industry. Companies are now incentivized to invest in lunar lander concepts, anticipating potential NASA procurement. engineers and technicians will find employment opportunities across multiple programs rather than being concentrated within a single entity. This expands the industrial base for space exploration, fostering redundancy and resilience. However, reopening the competition also signals a degree of uncertainty regarding Artemis timelines. The current schedule targets Artemis 3, the first crewed landing, for the late 2020s. Yet, delays have been a chronic issue. The Space Launch System rocket, NASA's heavy lift vehicle for Artemis, has experienced years of schedule overruns and billions in budget increases. The Orion crew capsule has also faced its own development challenges. Spacesuits required for lunar surface operations remain unavailable, and now the lander situation introduces another significant variable. Every delay incurs financial costs and erodes political capital. Artemis operates within a competitive funding environment, where resources allocated to lunar missions are unavailable for endeavors such as Mars missions, space telescopes, or Earth science research. Advocates must continuously justify the expenditure to both Congress and the public. High-profile setbacks, such as Starship test flights, culminating in spectacular explosions, provide ammunition for critics who argue that the funds could be better allocated elsewhere. The parallels to 3I Atlas are subtler but undeniably present. Both situations involve operating under conditions of uncertainty, with incomplete information and significant stakes involved. NASA must carefully weigh decisions regarding schedule margins, the extent of redundancy to procure, and the acceptable level of risk. An overly conservative approach could render the program prohibitively expensive, leading to a loss of political support. Conversely, an excessively aggressive stance could result in technical failures that undermine credibility. Astronomers face similar trade-offs. Allocating excessive telescope time to 3I Atlas would mean sacrificing valuable time for other scientific pursuits. However, allocating insufficient time might lead to missing a critical observation that could decisively resolve the case. Resources are finite, and choices invariably have consequences. The decision-making calculus involves a blend of technical assessment and intuitive judgment regarding where the most valuable opportunities lie. Public scrutiny impacts both endeavors. Artemis is a flagship program, highly visible to the taxpayers who fund it. Any setback inevitably becomes a news story, fueling debates about government spending and NASA's competence. While 3I Atlas is less expensive, it has captured the public imagination through speculation about its potential artificial nature. Both face the persistent challenge of maintaining public support through inevitable uncertainties and delays. The sociology of large-scale projects also reveals parallels. Artemis involves thousands of individuals across numerous institutions, each possessing distinct priorities and constraints. Coordinating such complexity demands effective leadership, clear communication, and established mechanisms for conflict resolution. Similarly, the global astronomical community must coordinate observational efforts, share data, and negotiate authorship and credit for discoveries. Human factors are as critical as technical considerations. There is also the question of legacy. Artemis aims to establish a sustainable lunar presence, moving beyond the symbolic flag planting and immediate departure characteristic of the Apollo missions. Such sustainability necessitates the development of infrastructure, the formation of partnerships, and the establishment of economic rationale that extends beyond purely scientific exploration. While 3I Atlas will not lead to sustainable interstellar missions, it significantly informs our approach to monitoring the continuous stream of objects traversing our solar system. Both initiatives represent foundational elements for more ambitious, long-term visions. The Artemis lander competition will unfold over several months, involving the submission of proposals, their subsequent evaluation, and a final selection process. In parallel, Starship development will continue. with each test flight refining the design or revealing new challenges. The interplay between competition and the primary contractor creates a dynamic where the success of either path benefits the overall program, although both paths require substantial resources and dedicated attention. For 3I Atlas, the analogous dynamic exists between observation and theory. Observers diligently gather data, while theorists construct models to explain it. Each informs and refines the other. Discrepancies between observational findings and theoretical predictions drive improvements in both domains. This inherent tension is productive, propelling us toward a more profound understanding, but it necessitates careful management of egos and appropriate recognition for contributions from both sides. Ultimately, both the Artemis and 3I Atlas investigations serve as crucial tests of our capacity to execute ambitious plans under conditions of uncertainty. They demand a delicate balance between boldness and prudence, optimism and realism. They require exceptional technical proficiency, but also adept political maneuvering, effective resource management, and unwavering resilience in the face of setbacks. The final outcomes will be shaped not only by the principles of engineering and physics, but also by the human organizations undertaking these challenging endeavors. Whether Artemis succeeds in landing humans on the moon within this decade, and whether 3I Atlas ultimately proves to be a natural phenomenon or something extraordinary, both narratives vividly illustrate the actual workings of modern science and exploration. They are often messy, expensive, politically charged, and fraught with uncertainty, yet they are propelled by a fundamental human curiosity and ambition that refuses to acknowledge limitations. This shared character connects them across vastly different scales and disciplines. Part 12. Vera C. Rubin. Observatory, First Imagery and the Dawn of the Rapid Survey Revolution. A revolution in our perception of the cosmos is unfolding at this very moment, and its implications for identifying objects like 3I Atlas are nothing short of staggering. The Vera C. Rubin Observatory, named in honor of the astronomer whose work provided critical evidence for the existence of dark matter, achieved its first light in late 2025. This significant milestone heralds the commencement of the Legacy Survey of Space and Time, LSST, an ambitious program poised to revolutionize our capacity for detecting and tracking transient and moving celestial objects. The design of the Rubin Observatory is purpose-built for wide-field astronomical surveys. Its telescope, situated atop Cerro Pachon in Chile, boasts an impressive 8.4-meter primary mirror and an extraordinarily large camera equipped with over 3 billion pixels. Together, these instruments can capture images of sky areas equivalent to 40 full moons in a single exposure. More significantly, the Rubin Observatory will repeatedly scan the entire visible sky every few nights, effectively creating a time-lapse cinematic record of the universe. This increased observational cadence fundamentally alters our capabilities. Traditional astronomical practices often involve revisiting the same celestial region, months or even years apart. The Rubin Observatory achieves the same coverage in mere days. When comparing images captured merely days apart, any object that has moved or changed its appearance immediately becomes apparent. Asteroids reveal themselves through subtle shifts in their position. Supernovae manifest as newly visible bright points. Comets, including those of interstellar origin, become discernible as fuzzy, moving objects distinct from the background stars and galaxies. The statistical implications of this capability are profound. Currently, we have confirmed the existence of only a handful of interstellar objects. These include Oumuamua in 2017, followed by 2 interstellar objects designated I-Borisov in 2019, and most recently, 3I Atlas in 2025. This amounts to a total of 3 confirmed objects over an 8-year period. Such a limited sample size renders it impossible to draw definitive conclusions about the broader population of interstellar visitors. Are interstellar comets common or rare occurrences? What proportion of them exhibit active outgassing? Do they possess unusual compositions that reflect diverse formation? Environments around stars in other systems? The Rubin Observatory is poised to answer these fundamental questions by discovering interstellar visitors at significantly higher rates. Projections indicate that once the survey reaches its full operational capacity, we can expect to detect dozens of such objects annually. This increased abundance will transform the study of interstellar objects from anecdotal case studies into robust statistical analyses. Scientists will be able to compare distributions of orbits, compositions, and activity levels. Anomalous objects like 3I Atlas, if they exist, will become readily apparent against the backdrop of more typical interstellar comets. Enhanced early warning capabilities represent another crucial advantage. 3I Atlas was discovered relatively late in its approach to our solar system, affording limited time for follow-up observations before its closest approach to the Sun. Future interstellar visitors detected by the Rubin Observatory will be identified much earlier, potentially years before their perihelion. This will allow for extended monitoring campaigns. Observing how an object's activity evolves over a broader range of heliocentric distances provides more precise constraints on theoretical models than isolated snapshots taken at only a few temporal points. The survey will also generate a comprehensive archival dataset. Every region of the sky will be imaged multiple times across various filter bands over extended periods. This extensive archive can be searched retroactively. Upon the discovery of a new interstellar object, astronomers can delve into the archive to ascertain if it appeared in earlier images before its true nature was recognized. These pre-discovery detections effectively extend the observational baseline, leading to improved orbit determination and a more detailed understanding of its activity history. Specifically concerning 3I Atlas, the Rubin Observatory became operational too late to capture its inbound trajectory. However, imagine if the Rubin Observatory had been operational since 2023. The object might have been detected when it was still 5 or 6 astronomical units away, visible though faint. Early spectroscopic analysis might have revealed the composition of celestial bodies before significant activity commenced. The entire progression, from dormancy to active states and even jet reversals, could have been continuously documented instead of being reconstructed from infrequent observations. This prompts a captivating inquiry. How many entities akin to 3I Atlas have traversed the inner solar system without detection? Our systematic search for interstellar visitors has only been underway for a few years. Prior to this, any object exhibiting a hyperbolic trajectory might have been observed but not identified as extraterrestrial. Investigations of archival survey data have uncovered potential candidates, objects whose orbital paths suggest an origin beyond our solar system, but the available observations were insufficient for conclusive confirmation. The Vera C. Rubin Observatory dramatically alters the detection threshold. Its sensitivity and observation cadence mean that fainter, smaller objects become discoverable. The population we are sampling shifts towards lower masses, potentially unveiling a different demographic compared to the few large interstellar visitors identified thus far. If hypotheses regarding artificial constructs hold any validity, larger sample sizes will either reveal supporting patterns or demonstrate that 3I Atlas and Oumuamua are rare anomalies with natural explanations. The sheer volume of data generated will be astounding. The Rubin Observatory will produce tens of terabytes of data each night, necessitating sophisticated automated pipelines for image processing, transient detection, and alert issuance. Machine learning algorithms will classify these detections, differentiating between asteroids, comets, supernovae, and variable stars. The stream of alerts, potentially numbering in the millions per night, will feed into follow-up networks where human observers will determine which events warrant more in-depth investigation. This automated infrastructure represents a paradigm shift in time domain astronomy. No single individual can scrutinize millions of alerts. Algorithms prioritize candidates based on criteria such as novelty, rarity, or alignment with predicted signatures. Intriguing candidates will be flagged for human review, and exceptionally interesting ones will trigger rapid follow-up with specialized instruments. The system functions as a global network for detecting and responding to cosmic transient phenomena. False positives are an unavoidable consequence of such a large-scale operation. Many alerts will stem from artifacts, cosmic ray impacts on detectors, satellite trails, or processing errors. The challenge lies in fine-tuning the algorithms to maximize true detections while minimizing erroneous ones. Overly stringent settings risk missing rare events, while overly lenient ones can overwhelm follow-up resources with false alarms. Calibration necessitates testing against known objects and continuous refinement as the survey progresses. For interstellar objects, the signature is distinct yet subtle. Their hyperbolic orbits with high eccentricity differentiate them from objects bound to our solar system. However, determining an orbit requires multiple observations over time. A single detection cannot definitively distinguish an interstellar object from an asteroid with an as-yet poorly constrained orbit. Automated pipelines must track moving objects across multiple nights, fitting orbits and flagging those whose parameters suggest an extraterrestrial origin. The human element remains indispensable. Automated systems can identify potential candidates, but human judgment ultimately determines which warrant the mobilization of costly follow-up resources. Spectroscopic analysis, high-resolution imaging, and intensive monitoring campaigns all require human decisions regarding resource allocation. The Rubin Observatory will amplify the discovery rate, but the astronomical community must proportionally expand its follow-up capabilities. Collaboration becomes increasingly vital. No single institution can afford to follow up on every compelling target. International coordination through networks like the International Astronomical Union's Minor Planet Center helps distribute the workload. Observers share data, coordinate to prevent duplication of effort, and collectively compile comprehensive data sets on transient events. The comparison to 3I Atlas is instructive. That object received intensive follow-up because its unusual characteristics justified it, but such decisions were made on an ad hoc basis, influenced by initial reports and growing excitement. With the Rubin Observatory poised to discover numerous similar objects, the community requires formalized protocols for prioritization. What criteria should trigger intensive monitoring? What distinguishes routine interstellar comets from exceptional cases deserving significant investment? Looking ahead, the era of the Rubin Observatory will likely witness many discoveries comparable to 3I Atlas. Some will be natural comets with interesting yet explicable properties. A select few might prove genuinely anomalous, challenging our current understanding and necessitating scrutiny, akin to that applied to potential artificial objects. The crucial factor is having established systems in place to differentiate these phenomena, allocate attention judiciously, and avoid both overlooking genuine anomalies and overemphasizing routine discoveries. This revolution is not merely technical, but also cultural. Astronomy is transitioning from small-team, single-target studies to large-scale surveys and big data analysis. This transition demands new skill sets, enhanced infrastructure, and innovative approaches to collaborative organization. The Rubin Observatory is at the forefront of this transformation, and its success will depend as much on human organization as on the performance of the telescope itself. For anyone interested in interstellar visitors, the coming decade promises to be extraordinary. The current trickle of discoveries will swell into a flood. We will ascertain whether Oumuamua, Borisov, and 3I Atlas are typical or unusual examples. We will refine our understanding of formation mechanisms, ejection processes, and galactic population statistics. And perhaps, just perhaps, we may encounter something that defies all natural models, something that compels us to consider possibilities we have previously only speculated about. The Rubin Observatory provides us with the instruments. What we discover is ultimately in the universe's hands. Part 13. The James Webb Space Telescope detects an atmosphere on a lava world. While terrestrial telescopes scan our solar system for moving objects, the James Webb Space Telescope, JWST, directs its gaze outward, studying planets that orbit other stars. Recent announcements from the JWST team include the detection of atmospheric signatures on ultra-hot, rocky exoplanets, worlds so close to their stars that their surfaces are molten. Although these discoveries may seem unrelated to 3I Atlas, they exemplify capabilities and techniques directly applicable to the characterization of interstellar visitors. The specific target, an exoplanet designated within the TI catalog or similar, orbits its star so tightly that surface temperatures exceed 2,000 degrees Celsius. At these extreme temperatures, rock vaporizes. Silicon and metals that remain solid on Earth transform into atmospheric gases, creating an environment that is utterly alien. JWST's spectroscopic instruments detected signatures of these vaporized minerals within the planet's atmosphere, corroborating theoretical predictions about lava worlds. The technical achievement is remarkable. The planet is located hundreds of light years away, appearing as a tiny speck lost in the glare of its host star. JWST observes these worlds during transits, which are moments when the planet passes in front of its star from our perspective. During a transit, starlight filters through the planet's atmosphere, assuming one exists. Different molecules absorb specific wavelengths of light, imprinting a spectral signature that JWST's instruments can detect. By comparing spectra taken during transits to those taken when the planet is not transiting, astronomers can isolate the planet's atmospheric contribution. This transmission spectroscopy technique is one of JWST's key strengths. Its sensitivity in the near to mid-infrared spectrum allows it to access wavelengths where many molecules exhibit strong absorption features. Water, carbon dioxide, methane, ammonia, and even complex organic compounds leave recognizable spectral fingerprints. The precision required to detect these subtle signals necessitates exceptional stability, calibration, and signal-to-noise ratios, all of which JWST provides. Now, consider how similar techniques can be applied to comets. A comet's coma, the cloud of gas and dust surrounding its nucleus, contains molecules that emit and absorb light in the infrared spectrum. Water vapor, the most abundant cometary volatile, has strong spectral lines within JWST's observable range. Carbon dioxide, carbon monoxide, methane, and other species are all accessible. By pointing JWST at a comet and obtaining a spectrum, one can directly measure its composition. For 3I Atlas, such observations would be invaluable. Optical spectroscopy has offered some clues about its composition, but infrared analysis is superior for quantifying volatile compounds. JWST could measure isotopic ratios, specifically the relative abundance of different isotopes of hydrogen, carbon, and oxygen. These ratios are reflective of the formation conditions, encoding information about the temperature and chemical environment where the comet condensed billions of years ago in another star system. Comparing the composition of 3I Atlas to that of solar system comets would test whether it formed under similar conditions. If the isotopic ratios align, it would imply that comet formation is a universal process, yielding similar outcomes irrespective of the stellar environment. Conversely, if the ratios differ, it would suggest variations in stellar nebula chemistry, providing insights into the diversity of planetary system formation across the galaxy. The discovery of the lava world also demonstrates JWST's sensitivity to unusual chemistry. Vaporized silicates in an atmosphere are exotic by earthly standards, but are a natural consequence of extreme conditions. Similarly, if 3I Atlas exhibited unusual spectral features, such as lines from metals or unexpected molecular signatures, JWST could characterize them with high precision. That precision is crucial when evaluating hypotheses about artificial objects. Extraordinary claims demand extraordinary evidence, and definitive spectroscopic data provides that evidence or conclusively refutes it. Scheduling observing time presents a significant challenge. JWST is the most oversubscribed telescope in history, with demand for observing time exceeding supply by factors of 5 to 10. Securing time to observe 3I Atlas would require convincing a review committee that the scientific merit justifies displacing other proposed investigations. For a routine comet, this is a difficult proposition, but for an object with potential techno-signature implications, the argument strengthens. Target of opportunity programs exist for time-critical urgent science, such as supernova, gravitational wave events, or newly discovered objects that will not remain observable for long. 3I Atlas could qualify, particularly near its perihelion when its activity peaks and its uniqueness is most apparent. However, directors' discretionary time is limited and highly competitive, meaning many deserving targets may never be observed due to a simple lack of available hours. Another relevant JWST capability is its high spatial resolution. At infrared wavelengths, JWST's angular resolution is excellent, potentially allowing it to resolve structures within 3I Atlas's coma at significant magnifications, mapping the regions where different molecules are emitting, and where gas is concentrated near the nucleus or distributed broadly, provides constraints on outgassing mechanisms. Jets would appear as localized emission features, while isotropic outgassing would produce smooth radial profiles. The lava world discovery also underscores JWST's role in astrobiology. The characterization of exoplanet atmospheres is a crucial step toward detecting biosignatures, such as the presence of oxygen and methane in disequilibrium ratios, which could indicate life. This search parallels the technosignature search that motivates the scrutiny of objects like 3I Atlas. Both endeavors seek evidence of phenomena beyond known abiotic processes, and both require rigorous standards to avoid false positives. Public engagement serves as another parallel. JWST discoveries, such as stunning images of distant galaxies or findings about exoplanet atmospheres, capture the public's imagination, thereby justifying the telescope's multi-billion-dollar cost and sustaining political support for space science. 3I Atlas, through its speculation regarding artificial origins, generates similar public interest. Leveraging this interest to support follow-up observations and broader search programs is an integral part of the science communication strategy. Advances in instrumentation drive progress in both fields. JWST represents decades of development, pushing the boundaries of technology in areas such as mirrors, detectors, cooling systems, and pointing control. Each innovation enables new scientific frontiers. Similarly, advancements in ground-based adaptive optics, spectroscopy, and time-domain survey capabilities are leading to better characterization of transient and moving objects. Investment in one area often yields benefits for others. The lava world finding also serves as a reminder of nature's inherent creativity. Extreme environments give rise to exotic phenomena that challenge our theoretical understanding, such as molten rock atmospheres, methane lakes on Titan, or subsurface oceans on icy moons. Each discovery expands the known envelope of possibilities. 3I Atlas, whether natural or artificial, adds to this growing catalog. If natural, it will provide insights into the diversity of interstellar comets. If artificial, it will reveal the existence of technology beyond Earth. Either outcome will enrich our cosmic perspective. Looking ahead, JWST's mission is projected to span years, potentially decades, provided the telescope remains operational. It will characterize hundreds of exoplanets, study thousands of galaxies, and observe countless solar system objects. 3I Atlas might be one of those targets, or it could fade into obscurity before JWST has the opportunity to observe it. However, the capabilities demonstrated on lava worlds and other extreme targets clearly illustrate what is achievable when we direct our most advanced instruments toward intriguing phenomena. The synergy between exoplanet science and solar system science is steadily increasing, with techniques developed for one field proving applicable to the other. Data from both domains contribute to broader questions concerning planet formation, chemistry, and the potential for life. 3I Atlas occupies a unique intersection of these scientific interests, an interstellar visitor carrying information about its home system as it passes through ours. The extent to which we can extract this information depends on available resources, prioritization, and a measure of luck with celestial and logistical factors. However, the necessary tools are now available, as JWST's recent lava world discovery has once again demonstrated. Part 14. LIGO and Gravitational Wave Community Milestones. While optical and infrared telescopes study light emanating from distant objects, another class of instruments listens to the universe through gravitational waves. The Laser Interferometer. Gravitational Wave Observatory, LIGO, along with its international partners Virgo and Kagra, continues its observing runs in 2025, detecting ripples in space-time caused by colliding black holes and neutron stars located hundreds of millions of light-years away. These gravitational wave detections may seem distant from the context of an interstellar comet within our solar system. However, the parallels in observational strategy and multi-messenger coordination are striking. LIGO's current observing run, designated O4C, commenced in mid-2025 following a commissioning period aimed at enhancing its sensitivity. Each upgrade brings the detectors closer to their design objectives, enabling them to sense length changes smaller than the width of a proton across kilometer-scale arms. This extraordinary sensitivity permits the detection of more distant, fainter sources, thereby increasing event rates from approximately 1 per week to multiple per day. When LIGO detects a gravitational wave signal, alerts are disseminated within seconds to telescopes worldwide. These telescopes then reorient themselves to search for electromagnetic counterparts, such as optical, X-ray, or radio emissions originating from the same event. This multi-messenger astronomy, which combines gravitational and electromagnetic observations, yields far richer information than either method could provide independently. The gravitational wave data reveals details about masses, spins, and orbital dynamics, while electromagnetic follow-up studies provide insights into composition, the surrounding environment, and the mechanisms producing light. The coordination required for this endeavor is intense. LIGO can only localize events to broad patches of sky, sometimes spanning hundreds of square degrees. Follow-up telescopes must meticulously search these entire regions rapidly before any transient emission fades. Survey instruments perform broad scans in search of new sources. Once a candidate counterpart is identified, larger telescopes are employed to obtain detailed spectra and light curves. All of this occurs within a time frame of hours to days, necessitating swift decision-making and international cooperation. This model bears a direct resemblance to the requirements for following up on interstellar objects. Discovery alerts from surveys like Pan-STARRS or the Vera C. Rubin Observatory trigger a cascade of confirmatory observations, including orbit determination and characterization, spectroscopic analysis, photometry, and astrometry must all be executed promptly before the object fades from view or moves beyond observation range. Resources are inherently limited, making prioritization essential. The astronomical community has developed protocols, informed by gravitational wave campaigns, for efficient coordination. One key lesson learned is the value of rapid response infrastructure. Having telescopes on standby or scheduled to interrupt their observations for targets of opportunity enables immediate follow-up. Manual scheduling can take days, whereas automated triggers can reduce this delay to mere hours or even minutes. For 3I Atlas, such infrastructure would have facilitated early spectroscopic and imaging observations that might not have occurred if observers had to submit proposals and await review. Another significant lesson is the importance of data sharing. Gravitational wave events are made public immediately, allowing anyone to access the alert and participate in follow-up efforts. This openness accelerates discovery, as a larger number of observers translates to better sky coverage and the utilization of diverse instrumentation. This model stands in contrast to older approaches where discoverers might retain proprietary rights to their data until publication. Open data policies, now standard practice in many scientific fields, owe part of their adoption to the success of gravitational wave astronomy. The statistical approach also presents a parallel. With dozens of gravitational wave detections, astronomers can study populations. What is the distribution of black hole masses? How frequently do neutron stars merge? Are there any gaps or peaks within the mass spectrum? Similarly, as the number of detected interstellar objects grows, we will be able to characterize their population. Are hyperbolic orbits uniformly distributed, or do they show clustering? Does composition vary systematically? What fraction exhibit unusual activity? Anomalies play a critical role in both fields. Most gravitational wave events align with theoretical expectations derived from binary evolution models, but a few exhibit peculiarities, such as asymmetric masses or unexpected spins. These outliers drive theoretical development, compelling refinement of existing models. 3I. Atlas, if it continues to exhibit anomalous characteristics, will serve a similar purpose. The majority of interstellar comets are expected to be unremarkable. However, the few that deviate from established norms will demand explanation. Technological development also links these fields. LIGO's vacuum systems, lasers, seismic isolation mechanisms, and data analysis pipelines represent cutting-edge engineering. Some of these techniques find application in other domains. For instance, vibration isolation technology, developed for gravitational wave detectors, enhances the precision of general scientific instruments. Algorithms designed for detecting weak signals in noisy data are applicable to radio astronomy and exoplanet searches, where signal-to-noise ratios are often marginal. The development of the collaborative community itself deserves attention. Gravitational wave astronomy necessitated convincing diverse groups to work together, share resources, and attribute credit appropriately. National laboratories, universities, and funding agencies across multiple countries had to align their efforts. This collaboration did not occur spontaneously. It required leadership, clear governance structures, and incentives that rewarded teamwork over individual competition. The success of this model provides a blueprint for other large-scale scientific initiatives. For 3I Atlas, no formal collaboration comparable to LIGO Virgo currently exists. Observers self-organize, coordinating informally through email and teleconferences. While this approach may suffice for smaller campaigns, it might not scale effectively as the field of interstellar object science expands. Establishing formal frameworks, data sharing agreements, and authorship protocols could enhance efficiency and mitigate potential conflicts. False alarms represent another shared challenge. LIGO occasionally triggers on events that are subsequently identified as instrumental glitches or noise fluctuations. Distinguishing genuine signals from artifacts requires rigorous statistical analysis and cross-checks between detectors. Similarly, transient surveys generate false positives stemming from cosmic rays, asteroids, or processing errors. Vetting these candidates is labor-intensive. Automated filters provide assistance, but cannot completely eliminate all erroneous detections. human verification remains a necessary step. Calibration is paramount in both domains. LIGO must precisely understand its detector response to accurately extract source parameters from gravitational waveforms. Likewise, photometric calibration enables astronomers to convert brightness measurements into physical flux values. Errors in calibration propagate and affect conclusions drawn about source properties. Maintaining calibration across multiple instruments and over extended periods demands meticulous attention. Looking ahead, the next wave of gravitational wave observatories, such as Cosmic Explorer and the Einstein Telescope, are projected to achieve sensitivity improvements on the order of 10 times current capabilities. These advanced instruments will be able to detect the mergers of cosmic bodies across the entirety of the observable universe, dramatically increasing the number of detectable events and facilitating highly precise examinations of general relativity. In a similar vein, forthcoming optical survey instruments and space-based missions are poised to revolutionize the study of small celestial bodies. They will enable the earlier and more comprehensive identification of objects originating from beyond our solar system. The underlying philosophical parallel lies in the pursuit of observing infrequent, transient cosmic phenomena that illuminate fundamental physical principles or signify unusual celestial occurrences. Gravitational waves emanate from the most extreme cosmic environments, specifically from the vicinity of black holes and neutron stars, where gravitational forces are at their zenith. Interstellar comets, conversely, offer insights into the conditions prevailing in other star systems, carrying valuable information about processes that are otherwise beyond our direct observational reach. Both avenues of research serve to expand the frontiers of our cosmic understanding. Furthermore, events such as the potential detection of the object designated 3 Atlas, alongside gravitational wave occurrences, share an inherent element of surprise. While we can statistically estimate the frequency of such events, their individual timing remains inherently unpredictable. This element of surprise is a powerful catalyst for public engagement. Individuals are drawn to breaking news about newly identified celestial events, driven by a natural curiosity to understand what each new revelation may unveil. This public fascination, in turn, provides justification for funding scientific endeavors, sustains the careers of researchers, and inspires the next generation of scientists. The convergence of gravitational wave astronomy and electromagnetic astronomy serves as a prime example of the potency of multi-messenger science. Each distinct type of cosmic messenger delivers unique and complementary information. When combined, these diverse data sets allow for a far more robust constraint of theoretical models than would be possible with any single messenger. As we continue to develop and integrate more observational channels, including neutrinos and cosmic rays, and potentially others, our collective network of understanding will become increasingly rich. While 3 Atlas itself does not emit gravitational waves, the fundamental principle of synthesizing diverse observations to construct a holistic understanding is universally applicable. Part 15 commences with a discussion of the dawn of new observational capabilities and enhanced spectroscopic power. It is imperative to address recent developments in the Chilean desert, as these advancements have fundamentally altered the landscape of astronomical research. In mid-October of 2025, a novel instrument commenced its operations, and its observational potential could dramatically influence our approach to future interstellar visitors. This instrument is named Foremost. While its name might evoke associations with administrative systems, it is crucial not to underestimate its capabilities. Foremost, an acronym for 4-meter multi-object spectroscopic telescope, is situated at the European Southern Observatory's Paranal Observatory in Chile. Imagine standing atop a mountain in the Atacama Desert, one of the driest regions on Earth, where the atmosphere is so pristine that stars appear as steady points of light rather than twinkling. Here, the Very Large Telescope, a name that perhaps reflects a certain pragmatic approach to nomenclature, is already active. Now it has been joined by a new companion. Foremost does not possess its own primary mirror. Instead, it functions as a supplementary instrument, utilizing one of the four 8.2-meter telescopes of the VLT. However, the contribution it brings is precisely what the astronomical community has eagerly awaited for years: extensive spectroscopic analysis capabilities on an unprecedented scale. What distinguishes Foremost from nearly all other instruments directed at the heavens is its remarkable capacity. While most spectrographs can only examine a single celestial object at a time, or perhaps a small handful under favorable circumstances, Foremost is capable of simultaneously capturing spectral data from 2,400 distinct objects. To reiterate, that is 2,400 spectra acquired concurrently. This is analogous to the difference between using a single fishing hook and deploying a net the size of a football field across the ocean. One is likely to ensnare objects that were not even being sought. The instrument operates through the deployment of fiber positioning robots. Envision 2,400 miniature robotic arms, each independently directing a fiber optic cable towards a different star, asteroid, comet, or galaxy within the telescope's field of view. This field of view itself is expansive, encompassing approximately 4 square degrees of the sky. For comparative context, the full moon subtends an angle of about half a degree across. Foremost can survey an area 16 times larger than this with a single observation. It divides incoming light into 3 distinct channels: low resolution for rapid surveys, medium resolution for detailed investigations, and high resolution for precise measurements of stellar composition. This represents not merely a new instrument, but an entirely new category of observational tool. Consequently, what are the implications for the study of small celestial bodies, including comets, asteroids, and other enigmatic visitors that traverse our cosmic neighborhood? The impact is profound. Historically, the primary constraint in astronomy has not been the detection of objects, but rather their characterization. The Vera C. Rubin Observatory, upon its activation, is anticipated to discover tens of thousands of new moving targets each night. However, mere discovery without detailed analysis yields little more than a compilation of celestial coordinates. Spectroscopic data is essential for determining an object's true nature, its composition, whether it is predominantly rocky or icy, the presence of organic molecules, whether it is actively releasing gases or dust, if its surface is covered in material or is bare rock, and if it is an asteroid, a dormant comet, or something entirely novel. This is where Foremost assumes critical importance. Its ability to simultaneously observe thousands of targets enables it to conduct extensive surveys of asteroids and comets, thereby building comprehensive libraries of spectral data. This, in turn, will facilitate the more rapid classification of newly discovered objects. It can also study the background population of solar system objects, providing essential baseline data against which to identify unusual occurrences. Furthermore, its capability to observe very faint objects, whether due to their small size, their distance, or both, extends our observational reach to populations that have been hitherto sparsely sampled, including trans-Neptunian objects, centaurs, and fragments resulting from recent celestial breakups, all of which become far more accessible. However, this is where the narrative becomes particularly compelling. Recall the events surrounding Oumuamua. By the time its interstellar origin was recognized, it had already departed our vicinity. We managed to obtain a few rapid, low-quality spectral observations that provided minimal insight into its composition before it vanished. With the arrival of Borisov, our observational preparedness was improved. Nevertheless, securing spectroscopic observation time on major telescopes is both costly and highly competitive. Every hour dedicated to studying a comet represents an hour unavailable for observing distant galaxies or exoplanet atmospheres. Observation time is rationed with extreme scarcity. Foremost fundamentally alters this dynamic. While it does not eliminate the competition for telescope time, it significantly amplifies the spectroscopic observational bandwidth available to the astronomical community. Should an interstellar object appear, or if an object such as 3 Atlas is confirmed and necessitates immediate follow-up observations, Foremost can be integrated into a coordinated response that does not require the abandonment of other critical scientific programs. It can acquire spectra of thousands of comparison objects to establish relevant baselines, while other instruments focus on the primary target. It can also monitor the object over multiple nights without monopolizing the observational schedule, thereby making rapid response spectroscopy feasible in a way that was previously unimaginable. Its surface. We could have monitored it for signs of outgassing or dust production, at detection limits far below what was possible. We could have compared its spectrum to thousands of known asteroids and comets, simultaneously looking for matches or anomalies. We might have answers instead of arguments. Now think about 3 Atlas. If it turns out to be genuinely interstellar, if those early velocity measurements hold up and it's confirmed as our 3rd visitor, we'll be facing it with a completely different arsenal than we had for the first 2. Vera C. Rubin Observatory will likely spot it early and track it precisely. The James Webb Space Telescope can provide infrared characterization, and Foremost can deliver spectroscopic data at a volume and cadence that was science fiction 5 years ago. If there are metallic absorption lines suggesting a surface we've never seen before, we'll catch them. If there are emission features indicating unusual chemistry or unexpected volatiles, we'll measure them. If the spectrum changes as the object rotates or as it approaches the sun, we'll document it. The timing almost feels intentional, doesn't it? 3 potentially interstellar objects in 6 years, and suddenly we're deploying instruments that were designed for different purposes, but turn out to be perfect for studying exactly these kinds of anomalies. Vera C. Rubin Observatory finds them. Foremost characterizes them. JWST sees what they're made of. It's like we're assembling a toolkit without quite knowing what we're building it for. And only now, as the visitors arrive, are we realizing what we've created. But here's the uncomfortable question that keeps me up at night. What if 3 Atlas is genuinely strange? What if the spectra come back showing something that doesn't match any known composition, or features that vary in ways natural objects shouldn't vary? What if we finally have the instruments to see clearly, and what we see doesn't make sense? Because that's the thing about better tools. They don't just answer questions. They reveal how much we didn't know. 3 Atlas may be the next big anomaly, or it may be a perfectly ordinary comet that happens to be moving quickly. We don't know yet. But emerging instruments like Vera C. Rubin Observatory, Foremost, JWST, and others are reshaping our ability to detect, verify, and possibly challenge our assumptions about what interstellar visitors can be. We're entering an era where we won't have to choose between finding anomalies and understanding them. We'll be able to do both. And that means when the next visitor arrives, and there will be a next one, we'll be ready.